a lot of people are a lot better than me at doing technical talks. So don't get me wrong, I love the science. I also like to try and provide a framework for thinking about the longer range scientific enterprise that we're part of. So check out this lofty title, Our Emergent Humanity from Local Interactions to Social Dynamics. I think this talk should be of interest to anybody who's wondering, what is it that allows humans to do what they do, to build the kinds of complexity in the world that we see, and ultimately then tying that back to the types of research that we're all doing, that this workshop is about, the EgoMotion. At the end of the day, it's humans that... Oh, okay, I could squat with it. I wish I had an EgoMotion tracker. So here's another interesting perspective. And I've been musing on this now for a few years, the fact that there are a few moments in human history where we look upon our own civilization and we say, my goodness, everything has changed again. And for those of you interested in science in general, when Darwin and co came along with their theory of evolution, that certainly changed the way that we looked at humanity. But a very big one happened in the last century when we finally took a photograph of our blue marble and recognized that everything that was humanity existed within effectively a thing that was incredibly precious and rare. And this, in fact, was from the photo from the Apollo 8 mission, which was taken on Christmas Eve in 1968. Coincidentally, 1968 is also the year when Xerox PARC was well underway developing the generation of computers that would ultimately lead to things like the personal computer, the Mac, and ultimately the iPhone that you probably have in your pocket today. And these things are going on, changing the world around us as we know it. But this was such a visceral example of understanding our humanity. Now, some years earlier, Frias Corinthi had pointed out that even though the world is very big and full of billions of people, and at this point approaching, past 8 billion, in fact, if you think of it from a point of view of connecting with anyone as a network phenomena, then effectively the idea that you're only separated by 6 degrees of separation between you and anybody on the planet is also a profound idea. So the idea there being that you know somebody who knows somebody who knows somebody who ... knows pretty much anybody on the planet. And with that in mind, you can say at once, we have seen that the world is both enormous and populous, but at the same time, with just a few hops between humans, you might be able to reach anybody's mind. And from a point of view of the scientific enterprise and anything else, for that matter, the idea that you're that close to humanity is something that you can hold quite literally in your mind and think about as if only you knew those 6 people, you could get to any mind. And of course, we're used to the fact that the technologies over the last 40 years have certainly helped us develop this concept into something which is far more reasonable. That is to say, every single day you use the internet, and we'll get to that in a second, connecting us across the planet. Now, another very important concept was introduced in the early 90s, which is Dunbar's number. So we've got the very big, we've got the connectivity on the planet, but we've got the fact that you locally interact with a very small group of people on an everyday basis. And Dunbar's number basically describes the phenomena that humans seem to have around 150 stable social connections. Made up of, a few, maybe 5 or so very close relations, and, maybe a dozen or so intermediate or otherwise, your close work colleagues, and on in layers or shells of people that you know less well, up to about 150 that you might, if you tried hard enough, list their names and think about their interactions with on a yearly level. And this is a dynamic network. People come into different layers of this shell all the time, and the interleaving of different people's effectively Dunbar set is the reason why, in fact, we can have everything we see today. Societies are formed out of those local interconnections between people into larger groups, into institutions, into nation states, into the planet as we know it. Now, This particular limit on our ability to reach people locally is something of a limit, of course, in our access to all of those minds on the planet as well. So, reasonably, the ability to reach those 8 billion minds through to 6 degrees of freedom ultimately is done through your local network. And the internet has formed that even more local network that allows us to chat with each other, over great distances with little to no cost. And this was, in fact, the Meta Facebook graph from, I think, 2012, when we were already connecting billions of people across the planet. Since then, Meta has got into a very different game, which is extremely exciting for us in the egocentric motion community. Wearables have emerged as a brilliant way for the extension of and enjoyment for the social media networks. That is to say, taking photos, sharing experiences is a great thing to do. And realistically, the ability to do that ever more when present in your everyday activities is something that allows us to share even more where we want to. So there's a whole set now of commercially available glasses, which, in fact, if I had to find out, let's do a quick poll, James. How many people here have ever tried a pair of Ray-Ban Meta glasses? Oh, it's almost a captive audience. That's nearly 90%, I'd say, which is a very good sign. My favorite ones are the Oakley Meta Vanguard, which internally we get to test, and great for cyclists and runners, etc. And we've got our first generation of display capable glasses as well, that if you go to a Meta store, you can try and order. Now, my own team has been working on glasses long before there were the commercially available ones for the purpose of researching the potential value exactly not for social media, but instead for furnishing AI with context of what's going on in your everyday life. And we're now on generation 2, and today we had our fourth tutorial on the ARIA egocentric systems, including the hardware devices. Now, that has furnished sort of this triad of topics, which I think at least 2 of them, to anybody, should be very familiar. It's interesting if all 3 are to everybody. Everybody in this audience is almost certainly either in robotics, working on contextual AI, that is to say, furnishing context for the current internet scale LLM type AI so that it can really understand your physical reality, or you may be in the other kinds of human sciences, the social sciences, social psychology, maybe even health, various things which really look at what humans are doing rather than trying to create systems that replicate what humans do. Let's take a quick poll. Who here is in robotics? Excellent. That's about a quarter. Who is in contextual AI? Amazing. A little bit more. Interesting. Just over a quarter. And human sciences, which is good. We have 1 person, which means that all those fractions don't add up to 1. That's okay. Not everybody has to vote on that poll. The reality is that only 1 person put their hand up on the human sciences side, which is why I'm going to focus on that in this talk. I really think it is the area that is not as established, especially for the computer vision community, for where the biggest value is and breakthroughs to be had. And the reason for that is because ultimately what we've seen over the last 2 decades is that all of that infrastructure that got built for humans to share their experiences through social media and the web in general is how data was provisioned to enable the current generation of AI to be built. And on top of that, the current robotics capabilities that depend on that. Now, that's a profound point because, of course, if you were setting off in, let's say, the 1980s and said, I want to do a robotics project at scale, it'd be very difficult to imagine getting funding to build the internet and then the World Wide Web and then social media and furnish a few mobile phone companies and all the telecom services that are necessary to enable that. And yet, when we think about modern AI, it did depend on all of that. It's just a point of view of the cause and effect in reality, so we have this infrastructure and now it's very useful for getting experiences from humans. Now, I think the future actually is even brighter when looking at what it is that humans do just as an enterprise in understanding ourselves. And I think the more that we get into robotics and contextual AI, the more important it will be to actually understand what is valuable to humans and how we do it. So I want to start by zooming out and ask if we could see any kind of shape and motion in our lives at a macroscopic level. This workshop is, if nothing, about the very detail-oriented view of humans interacting with each other and the environment. But we can take a slightly broader view. This here is a day in the life of Americans from around 2014, furnished with data from a mass-scale US study. And it basically looked at what Americans do throughout the day at a minute scale. So people were tasked with basically filling out forms on the minute, all the way through the day, and that data is freely available online. You can have a look at this animation that was from Nathan Yao. I'm going to get it started. He developed this in 2015 to try and demonstrate the kind of rhythms of the day of the life of your American. It's hard to say average, because what you'll notice here is that a lot of people, each point here is an individual sample from 1,000 Americans. And hopefully on the screen you can see that there are things like, well, sleeping is a very important thing, and most people start the day by actually finishing sleeping, and then they get on through their various different things, from personal care to doing some sort of sporting activity, household, childcare, ultimately traveling to work. Very smartly, Nathan put traveling in the middle of this diagram that allowed the transition function between the different activities to sort of quite naturally flow. Actually representing and visualizing this stuff is an interesting topic in itself, because it's such a high-dimensional thing. Even choosing, in fact, the activities around the edge here is a non-trivial thing to do, because there's a tail of a distribution that people do that may make up a very large fraction of everyday activities. As you hopefully have seen, we're getting to the end of the day, and after people have done whatever they consider leisure, they get back to bed. Now, some folks are still working, and they seem to go from work straight to eating and drinking in bed. I think this characterizes a lot of people in our field, and that's really a day in the life of Americans. So there is something of a shape, and there is something of a dynamics, and if you stare at this diagram enough and think about different ways of visualizing it, you can certainly pull out different things that say, my goodness, in some ways we are very predictable, aren't we? We've all got to sleep at some point. We've all got to get up and clean ourselves and eat and do our daily activities, including work for most of us and so on. So that's interesting. We are kind of predictable, aren't we? Okay. Now, another way of looking at our lives is through story. And I like this in particular because it goes to an even sort of grander view of what we as humans kind of endeavor to do. And you can say, well, we live our lives, but again, when written out in stories, what we find is a collapsing of very complex individuals into things that actually are very familiar. And Kurt Vonnegut epitomized this with the shape of stories idea. He basically said, all stories have got a beginning and an end. And, the protagonists in these stories kind of can be thought of as having sort of like at any point in time an amount of fortune. It's either good or it's kind of bad. It's going well for them or it's not going so well, right? And so then he went about and he studied, all the different stories, and not just, purely fictional ones, but ones that seem to be narrations of people's lives. And he basically said, look, there are these shapes and they seem to reoccur. And we'll just go through a few of them and see if you recognize them. The first one, quite famous, is called Man in a Hole. So this is a person who's just going about their life quite happily, and suddenly they fall into a hole. Of course, that hole is not very nice. It's dark. It might have been painful to get in that hole. But luckily, they get out of the hole, and that's the end of the story. Man falls into a hole. Now, the interesting thing about this particular story is this subtle point that at the end of getting out of the hole, somehow he might actually be better off than he was in the first place. That's a good story. Now, another story, what Kurt Vonnegut said, boy meets girl, but actually is about anything that you kind of find and fall in love with and then lose. Basically, you begin absolutely neutrally in life, loving nothing, hating nothing. You find something you love, you lose it, and luckily you get it back again. That's a great story. People recognize that story anywhere? I'm sure you do. Okay, there's this terrible story, but certainly some people might feel like they live it, which is where you start off in a very bad situation and it just gets worse. And there's no end to how bad it can get. It sort of maps onto Kafka. And then this one, the most famous of stories, is Cinderella, which is a bit more complicated, but it basically says, you're born into hardship, and through some sort of luck or intervention, things get better for you. And they get better and they get better, and it's going really, really well. And then, boom, it goes really bad. But luckily, it goes well in the end. And that's a good story. Everyone can feel good about that. That's Cinderella. Now, the shape of these stories, they're kind of interesting. They're analytic-looking things. They look like functions, and they, in fact, are, right? In fact, what's going on here is some very interesting compression of reality by Kurt Vonnegut into like one axis. He calls it fortune. And he basically says, look, you can look at all stories through these axes. Now, that's an interesting thing, because again, the question is like, how predictable are we when seen through just this one dimension? Okay, we're at a very, very big scale of human interaction here, right? Social dynamics. Okay, let's zoom in a bit. What's in a day in the life of an individual? Well, for at least a few years now, I've been getting up on stage and saying, look, if you did have a device that was with you when you wake up and you went through your entire day, however it is, you could start to furnish a lot of context to AI with that. It'd be very, very useful. It's also very interesting if you could capture it at that level. The surveys that were filled in by those thousands of Americans, was arduously filled in by hand. If we could, in fact, get a science going where we're able to get that automatically, of course, there's a lot that can be done with that. But the thing is that when you ask the question of a device and sort of a representation of reality, there seems to be sort of no end to what you might need to fill in and say, I need to represent this. Well, even when brushing my teeth, how exactly do I represent the brushing of my teeth? To what fidelity do you, think you might need to know whether or not I got my left molar covered and the top one, and how much toothpaste was on my brush anyway? And it goes on and it goes on. And this is a very interesting and profound problem for us doing tracking and activity detection, because in some ways there is no end to the fidelity that we could, in principle, represent. And you don't know what might be important context at what level of granularity until you need it. And then retrospectively, you can say, oh, that was useful context. But if you didn't capture it, you don't have it. So this is an important dilemma. And the level of subtlety may be at the level that we are indeed looking at in this workshop. So, just exactly how is your hand or finger moving? What is the placement of your foot during this exercise routine? What is your heart rate? Where exactly are you looking? Are your pupils dilating? There's no end to the level of granularity, and it may all be important. Now, that's just capturing the signal, but I want to go further. I want to ask and think of this as, can we capture the cause and effect in reality? It's different from the state, and it's kind of in some ways very related to activity and action, but we often get these subtly confused. The cause and effect different to necessary correlation, many, many correlating factors, but what is the cause and effect that's going on? Now, I can find no better example than this episode of Friends, which is called The Wink. Who's any Friends enjoyers in here? Anybody like Friends? Sorry, Seinfeld. Thank you, Logan. I'm very, very tired. That means that there's at least 10 people in here. The Wink is a very fun episode. I hope you go and actually watch it on YouTube for free. I've just pulled some frames out here for the purpose of this academic example. Now, what happens is that Jerry is sitting in the diner and he's eating breakfast with his best friends, Elaine and George, and for whatever reason, he's eating a grapefruit that morning. And you can see this very subtle interaction of him digging into the grapefruit. And anybody who's had a grapefruit will know that indeed, depending on the grapefruit and how you've prepared it, have you rolled it? Is it the right time for this grapefruit to come out? Then using a spoon, is the spoon sharp enough? It can be a very difficult task. And in this particular instance, then that grapefruit, which is a very subtle action, if you imagine it from a point of view of detecting it, shoots some juice into George's eye. And this is unfortunate, and we'll see why. George, later that day, goes to work, and unfortunately, he's still got a bit of an irritation in his eye. And all good so far, these things happen, right? Well, his manager comes into the office and asks George for some advice on one of his colleagues that he's a bit worried about. And if you know George at all, he's a consistent worrier, if nothing else, and he doesn't want to necessarily get this wrong for his manager. And starts to give an answer to his manager about what his colleague may be up to. And you can see this like absolutely standard expression from George here. George starts to give an answer until suddenly he winks. He winks at his manager, the wink, which causes his manager to think that what he is saying must be some sort of truth that must be hidden from the real truth. So when you see a wink, you know that there's something else going on. Now, as it is, the cause and the effect in this case are quite far apart, understanding that one thing in the end caused the other through this chain of biological interaction with a person's eye membrane that caused an irritation. Now, this is actually a very funny program, and I know that I did a very good job in not making it funny at all, so go and watch it. But the point is that is cause and effect played out. And I thought I would have a look at how current Gen AI is doing. And so I asked Meta AI and Sora, I said, okay, some friends are at dinner together and they're enjoying themselves until one of their friends is rude. And so their friends give him the look. And I think we can all agree they are giving him the look. It's done a very good job of generating that. Now, I don't think this is necessarily surprising. I do think it's interesting just how accurately they've been able to generate this eye gaze, given the kind of like global context of the text. What was more astonishing is that I then asked it to turn it into a video and simply predict what comes next. And this is what happened, which is definitely the look. And of course, it may be the case that a fight is about to break out here. But this says something really quite amazing. It says that our generative AI models trained on internet scale data understand things as subtle as the look. They understand these cues in ways that I think we would have all imagined only 10 years ago would have been extremely difficult to capture and generate. Now, I put it to you that whilst we can generate video like this, we actually can't detect when it's actually going on between humans. So whilst you and I can detect the look when it's given to us, and I think I said this morning to the group where I was giving a version of this talk, anybody who has children will know the look that they can give to their children, or if they're a guardian, when the children are doing something they want to stop. And without intervening at all, but except by moving their eyes, that child will know that they need to stop what they're doing. It's very interesting. We do it at a very young age is what that means. The thing is that we don't seem to be able to have devices that can do it. And so therefore, if our devices can't understand that, then our AI can't understand it from our perspective, even though it can generate that kind of seeming behavior. So I put it to you that actually getting to this level of granularity, there is the constituent primitive that allows cause and effect over time, is kind of like the next frontier of our egocentric motion problem to solve. And this brings me to the cause and effect graph. Now, at the top of this graph, I've simply put down some sort of primitives. But as I say, there's no end to the level of granularity that may need to go there. And I think in the modern era, we actually just think about latent spaces where they could decode to things like moving, writing, winking, looking, and so on. But I like to imagine that maybe in the next few years, we've got to a point where with our egocentric devices, we're able to track the motion and detect the activities to such a granularity that we can really start to form these chains of cause and effect. And in doing so, even though this is a very small example of just a few work colleagues working together, I'll leave it to you to try and imagine what on earth this interaction is, by the way, that there are actually patterns that can emerge over time. And if you think of it not just as like a few people interacting, but hundreds of thousands, entire society scales, and not just over a few minutes, but actually over years, then we can see the potential for a new kind of human science where we really put to task the mathematical tools that have been used, for example, in internet scale media and use them in physical reality. And I'm quite interested to imagine what kind of dynamics we might find and what we call them, because they probably map onto things that we socially do understand, but we can now perhaps track them. So we've got these three areas, and I certainly am interested in us doing more with the human sciences of things, and I believe that we're building the right tools for it. That brings us to Area Gen 2. Area Gen 2 has a lot of the stuff that solves many of the problems with Area Gen 1. It has a lot better sensing on board. We'll get to that in a second. But it also has onboard computation, which means that a lot of the signals can be computed on the device, for example, eye tracking and hand tracking and head pose. And this allows the data to be stored in this extremely compressed form, but also to be used for real-time interaction, for example, with AI or with analysis tools. It has extremely wide fields of view, so there are 4 computer vision cameras in the corners of the frames, and 1 very wide field of view, very high resolution RGB camera. In fact, the same RGB camera as is on the Ray-Ban Meta devices, we just put a wider field of view lens on there. Now, the CV camera itself is a tremendous piece of engineering. We've been able to create a sensor with 120 dB dynamic range, which is actually slightly better than the human eyeball can see. And it means that even when the lamp is on, our CV cameras can see the filament. So it can both see the low lights, the shadows. You can see, in this case here, the outside window where both the tree and the light bulb and the filament of the light bulb are on. The RGB camera, of course, gets saturated, as is common. Now, this is very much a superhuman capability. The new device also has stereo cameras. So in this example here, and we're going to be doing live demos of this at the booth, I think, is that from tomorrow, James? Yeah, so do come along and see all of these live demos, actually. We can generate very high quality depth maps in real time. And that's great because a lot of the robotics applications really do like metric depth. In fact, we were just showing that live in the room just a moment ago. So yeah, go along to the Meta booth to see that live. Okay, as I say, understanding what humans do, I think, is the thing that is very new. And in this case, understanding, for example, how humans see through foveated vision leads to the ability to look at eye gaze foveated capture, which again is highly compressive. That is to say, we don't necessarily need to capture all of the data of the wide field of view at the highest frame rates. We can just ask, what is it that the human can actually possibly see, if that is what we're trying to study? And that can be greatly advantageous for building data sets that are much smaller when at scales of days, weeks, months, and years. Lingni, hopefully, is going to show you the absolute best of the bunch of the EgoMotion full body prediction systems that have been built around the ARIA data sets from Nymeria and the updates there. And the sort of latest and greatest of building scene graphs for tracking interactions with the environment is, I think, the hottest thing that's going on across the wider discipline of EgoMotion and activity detection with the more classic areas of object tracking. So certainly I think we're going to see more of that in the next few years. ARIA Gen 2 also enables us to do alignment between devices. This means that if you've got a capture setup with a dozen or so devices, you can time align the data streams extremely precisely, microsecond scale. And if anyone who's tried to build a capture studio in their lab from GoPros and then compress through MP4, you'll know that it's actually a very big deal to get proper time alignment at the microsecond scale. Ultimately, I feel this is going to lead to a new kind of revolution in data from distributed sensors. So we're used to a single camera, we're now used to video, but we're not used to the idea that actually, just like we humans exist in groups, our devices will exist in groups, be it human-worn wearables or robots with humans or robots with robots. And that means that the data sets that we can start to look at and analyze, be it for creating new algorithms that are just better than the individual robot may have, or the individual wearable pair of glasses may have, when they share access to their sensor streams in consented ways, you can imagine the kind of superhuman capabilities that can become possible. And that's very exciting. And of course, even though we're looking at egocentric motion, in reality, these wearables allow us to furnish exocentric behavior as well. I think we might see some of that from Lingni's talk as well. Very exciting stuff. With that, I'm sure I am fully over time. So thank you for having me. Thank you to the organizers. And James, I think you're back on.
So hello everyone. Sorry for the delay just now. So my name is Ziqi Huang. I'm currently a PhD student at Nanyang Technological University in Singapore. And Ziwei Liu, who is my PhD advisor, who was going to give the talk today, but he still hasn't got his visa. So that's why I'm here today to be the proxy presenter for this talk. So we know this workshop talks about EgoMotion and egocentric vision. So why do we need egocentric vision? First, it's very natural that human experience and cognition is from the first person's point of view. How we look at things, how we attend to different things, and how we navigate in the space. And also, egocentric perception provides a better context for interaction. For example, when we manipulate objects, we are observing it from the first person view. And also, when we do social interaction, we are observing other people from our own eyes. And egocentric perception actually has some very important applications. For example, for personal AI assistant, if we want an AI assistant to be with us and help us remind us about things and look through our own eyes, then it has to be egocentric to observe what we are seeing every day. And also, even further for embodied AI or robotics, how the robots or the embodied agents, they observe the world is naturally egocentric. They are seeing their robot arms, and the cameras can be installed on a humanoid or even on the arm themselves. So for egocentric perception and understanding, we first want to talk about its very important application in being a life assistant AI. It's something that accompanies us as a life assistant as if it were a butler. Imagine if there were a companion or a memory keeper, although it's AI, it can record and summarize our personal experiences. And it can also help the user to, for example, recall some moments that they forget or to help them find the lost items. For example, I purchased something today, but I don't know how much it is, what the price is. Then this personal assistant AI who has been like recording your life and analyzing what happens in the past few days can help you like retrieve your memory and tell you how much the thing is. And a life assistant can continuously observe the user's behavior patterns and daily routines. In this way, it knows the person better, it knows us better, and it can learn our habits and schedules, and also can proactively remind us of things. For example, I have a meeting to attend, just like the Apple reminder, it can remind us of the upcoming tasks or some important events. So EgoLife is this great project about building towards an egocentric life assistant. And Jian, who is also online with us today, linked via Zoom, he is the project lead and first author of EgoLife. So if later the audience has any questions about EgoLife, feel free to talk and interact with Jian. So if we use one sentence to summarize the work EgoLife, they were inspired by some reality show, like the series and the TV shows, and they invite 6 people who do not know each other before to live together in the same house. So there was a house, and they just stay in the house for 7 days. And each one of them wears a metal area glasses almost all day long and around 8 hours a day. And in this way, we can record extremely long egocentric video data set. So it's like recording 6 people's life over 1 week, almost nonstop. And in order to collect the data set, this is the setup. So there are 15 fixed cameras in the house to get the exocentric capture of the videos. And there are also 8 cameras among the 15 cameras. There are 8 on the first floor and 7 in the second floor. And they are also synchronized with 6 egocentric videos from the volunteers. So the volunteers are wearing the glasses to capture the egocentric views. And there are also other signals being captured, such as waves and other modalities like audio, of course. And if you want to take a closer look at the EgoLife house, you can visit the EgoLife website. Just Google EgoLife. So in order to have the 6 people to really do something and have a concrete life goal during the week, we ask the participants to collaborate and organize this party called the Earth Day Party at day number 6. So that among this week, they should have some diverse but coherent activities going on. They could have meetings and they could go to shopping in day 1 and prepare some singing and dancing rehearsal in day 2 to prepare for the party, and also practicing some, for example, cooking in day 3, and so on. So in this graph, each different color is a different type of activity that the 6 people do over the week. Of course, they also do social interaction, which happens very frequently, and also housekeeping, like they are actually living in the house and throughout the week. And of course, like shopping and dining to meet their living requirement. And over the 1 week, the 6 people, they gradually get familiar with each other so that the interpersonal dynamics also can be traced, like how people interact and who interact with who else more frequently. And with those extremely long and life-oriented egocentric videos, we also designed 5 different types of life-oriented QAs, like question and answers. And most of the QAs, they require a model or like a real human to really trace back more than 2 hours ago to get the correct answer. And here are some examples of the QAs. For example, there is one called Event Recall. For example, it asked, what was the first song mentioned after planning to dance? And usually when days and hours go by, people just forget. But with this egocentric life assistant, it can try to answer this question. And also, for example, on the right-hand side, the task master. For example, when I walk past a store, I remember I need to buy something, but I suddenly forget what I was going to buy. So some life assistant can remind me that, for example, I should buy a gallon of milk because I found it's out of storage in the fridge this morning. So it's kind of like a reminder of the task that you are going to do. And there is also habit insight. Habit insight are the questions try to find my hidden habit based on my behavior pattern in the past few days. And of course, there is a relation map about the social interactions. For example, it can ask, Shuri is playing the guitar right now. Who else usually join us playing the guitar together? And the life assistant can track your personal social interactions and help you summarize, retrieve, and answer this question for you. So it knows you better and knows your friends even better. So here is an example. The question is, how much is the egg? They are preparing like for the dinner and in the kitchen, and they bought some egg and they wonder how much is the egg. And in the video, in day 4, Jake cracks egg into a bowl and it wonders what's the price. So this is the type of question and QA designed in the EgoLife QA benchmark. Okay, so this is the overview or the main framework of the Ego Butler, the life assistant that helps each person to record, retrieve, and remind them of things and answer the questions. So the Ego Butler architecture has several components. First, on the left-hand side, we can see there is a captioning stage with Ego GPT. And this part is actually the you can consider it as a data labeling stage, where after we have recorded hours and days of videos and audio, Ego GPT is actively and continuously labeling the data, providing captions for the data and the audio to record what has happened in language. And on the right-hand side is actually the question answering stage with EgoRag and Ego GPT. So this is how the live assistant is helping the person to record their memory or provide live assistance. For example, here the question is, what breakfast did we eat in the past 3 days? If I want to try something new, what is the recommendation? And given this question from the user, the Ego Butler framework will first extract the keywords. For example, it's about breakfast and it's about in the past 3 days. So those two are the keywords. And then based on those two keywords, we are going to try to retrieve some evidence, which are the relevant video pieces among the very, very long hours and days of videos. So the second step is the memory retrieval stage. And this is done by the EgoRag. And this memory retrieval stage is actually multi-level. So first, it will do for example, a day level location. For example, for the past 3 days, then we don't have to look at day 4 or day 5. And then after this, it will do a more fine-grained level of retrieval to actually get the evidence of what happened, what was happening during the breakfast time. So after obtaining the evidence, which are the relevant capture data, this evidence will be the actual input fed into EgoGPT in order to answer users' question. And EgoGPT will basically do a OmniVLM-like manner to answer the question. So it says, in the past 3 days, breakfast was either skipped or combined with lunch. That happens a lot for the research people. And 3 days ago, we made pan-fried pancakes, and next we had pizza. So it knows what people had for breakfast over the past 3 days. And yesterday meal featured Chinese pancakes and dumplings. So for new experience, EgoGPT recommend try some dianxin and some Japanese food. So this is how the Ego Butler system works. It can continuously label the data, record what happened in your life over the past few hours and days. And when you ask Ego Butler a question, it can do a multi-level retrieval to retrieve the relevant evidence from the data you record. And then based on this evidence and the question asked, it can provide the answers and give recommendation or reminders to make your life even better. So for the model, for the EgoGPT model, it's built upon the Lava 1 vision model. And we extend the Lava 1 vision model from vision only towards, from a vision language model towards an Omni model, which can also accept audio input at the same time. And the Lava 1 vision model, it was originally aligned with the Qianwen series of models. So here is a performance table of the EgoGPT 7B model on a series of classic egocentric datasets. And we also have this curated Ego IT dataset. This dataset is curated from 9 different classic egocentric video datasets, and their annotations are also used to generate the captioning and QA instruction tuning data in order to fine-tune EgoGPT. And for the Ego RAG component, it's actually boosted by it's in-depth, like for in-depth egocentric video familiarity, and it also accepts audio input for better comprehension. So powered by the EgoRAG, which is the retrieval module, and the EgoGPT, who can do the data labeling, captioning, as well as the question answering, they jointly enable week-long memory retrieval. So if you ask anything about what happened in the past 1 week, it can locate the evidence. And it can also answer complex and long horizon questions. And the grounding is relatively robust and context-aware. However, with all those merits presented by the EgoLife, EgoVLA system, there are still some rooms for future work. For example, just now when we mentioned to do the retrieval, it was a multi-level retrieval. For example, we locate the coarse grain time range first and then do a fine-grained search on the exact evidence piece to retrieve. However, this retrieval process is one time. Like the workflow and the logic to do the retrieval is just one forward time, and one-time retrieval can fail sometime. So it might help to utilize some agentic search in order to better and more robustly locate the evidence used for the QA. And later we will touch on this Ego R1 work, which exactly solves this problem. And also, there could also be some better person identification modeling. And for the behavior pattern tracking, maybe building a habit and behavior pattern engine for continuous insight generation would also be great to track different people's behavior patterns and what they like, their hobby is. Okay, so in summary, EgoLife is an egocentric life assistant, and what's special about it is that it records extremely long videos. It's egocentric and it's also interpersonal. There are 6 different people interacting together, and it's also multi-view. Like each one of the participants, they have cameras in their glasses, and there are also exocentric cameras installed in the house. And it's naturally multi-modal. We record videos, audio, and other modality of signals. And it's also about really about daily life. So it's not about specific sports or other activities. It's about daily interactions, how people cook, shopping, interact, and prepare for meetings and parties. So feel free to visit EgoLife AI, this website, to know more about the EgoLife project. And this is presented at CVPR 2025. So just now we mentioned for the to process very, very long range egocentric videos, the retrieval, if we only do one time, it could fail sometime. So we also take one step further to do better long-term reasoning in the memory retrieval and QA process. So this comes to the second work, Ego R1. So the challenges with existing event-based egocentric video understanding, first of all, it's very long. It's very long horizon spanning from days to weeks. And it's like natively multi-modal. It has audio and video, and it's not an easy task to like retrieving like both video and audio modality at the same time. And also, the event queues are very sparse in time. For example, sometimes the important queue to answer the question only happens within seconds or even half a second with a hand wave, or like with a particular frame where it shows some text on the screen. It's very detailed in time and space. So the cues is actually very sparse. How to accurately locate them and take a closer look, that's really a challenge so far. And when modeling long video perception, existing pipelines are often relatively rigid. That means it's just a predefined workflow from end to end. And when doing video sampling, often it's sample the video frames at a uniform space. So to address all these challenges, EgoR1 was proposed. It's an agentic framework, and it's used to observe very, very long, ultra-long videos and then decide which tool we can call in order to perform hierarchical retrieval and to answer the questions that the audience have. Sorry? 3 minutes. Okay, sure. So maybe I will skip some of the details and to let us know more about the other works we also work on. So basically, EgoR1 is a framework that perform reasoning in a chain of thought like manner, but instead of doing chain of thought in the text domain, in the language domain, we do chain of thought through the toolkit calling. So it's like in each step of COT, it does some reasoning thinking, and then it acts by calling the toolkits whether to observe the video again, or we call another tool to take a closer look at a particular frame with a zoom-in view, or should we go back to the original hierarchical search to locate another day. So it's a dynamic workflow to really retrieve from very, very long videos in order to answer the user's question when using the live assistant. And on top of, so this is the pipeline. It's using SFT plus RL with GRPO. It's a two-stage pipeline to make the model know how to reason and dynamically call the toolkits. So on top of perception and understanding from the egocentric's point of view, it's also important how to really see and move and act so that we can take one step closer towards really actioning and embodiment. So in this work, we propose a new task where not only generating human motion or egocentric video, we try to generate both of them at the same time. So in the Ego Twin framework, I can jump to the demo video to make it more intuitive. So the task is basically given the text instruction, pick up the towels from the back box. The model is tasked to generate the egocentric video as well as the human motion at the same time. And we designed this task because it's interesting to know how the human motion action would reflect in the egocentric first-person view videos, and how the videos would also indicate what motion was taken so that we can navigate in this way, or the objects were manipulated in this way. And the Ego Twin framework, it can do, the first thing is text to both motion and video at the same time. And since it adopts an MMDIT framework architecture, it can also treat this motion not as output, but as the noised input, so that it can take the text and motion as input and generate the video. And just one last work to share is about generalization in human motion generation, because in human motion generation, currently the scarcity of data or generalization is still a challenge. And this work will be released online by Ziqi in a couple of days. And it's a quest for generalization generalizable human motion generation, and we study both data, model, and evaluation. So there are data sets in not only human motion, but also from the rich web videos, because videos also provide generalizable capture of different scenes and motion. And there is also model which unifies video and motion generation priors. And also there is a motion bench, M-bench, which is a hierarchical benchmark in multiple dimensions to evaluate human motion generation. So here are some demos of the human motion generation results using Emergent. So with that, I would like to conclude the talk due to time constraint, and we hope with all these efforts from the community, we can try to see and act and really learn from the first person just like us. And if we still have time for questions, for example, for the Ego Life project, I think Jian is online to talk to us.
So I'm really excited to talk about this work called iRobot, learning to look to act with the BCRL perception action loop. And so let's dive in. Okay, so as you might have heard of, this is a quote from J.J. Gibson. We perceive in order to act, and we act in order to perceive. And so a lot of the things in computer vision is starting to work. And I really think this is kind of where I started, why I think vision is really cool. And I think this is a really good time to go back to this motivation of the reason why we want to do vision is so that we can actually act. And we move so that we can actually see better. And so this idea of active vision is an old ways of doing vision actually in the 80s. And the reasons why this is really relevant is because the moment you're embodied, you just don't get to see everything at once. I think the computer vision community, because the problem that we try to solve are really too hard, like trying to reconstruct a video from an internet, we try to solve it with everything we can. And then it's good that we now can solve somewhat of these problems. But then you forget that once you're actually embodied, you really don't get to see everything. So you cannot do any of the batch processing. And, this really came light to me when I had my baby because, she's really taking the world as one step at a time. And this is actually, I think, is a blessing that we actually don't get to see everything at once. I think then we would be this omniscient being. And it's a blessing in disguise because it makes us actually have to be more intelligent. And I think this embodiment thing, is the real bottleneck that we need. And of course, egocentric research kind of captures this behavior nicely. But today it's actually kind of more about how to really act, do some active perception. But since not everything is laid out for you, you have to make sense of the little bits you see. And we worked on this work called Cuter, which is an online SLAM or 3D 4D found model that is able to make predictions about the underlying 3D scene in a streaming manner. And I think that was also kind of inspired by this embodied setup that you actually have to take one scene at a time. You have to make sense from the little bit you see, and then you make decisions or actions to maximize useful information. And I think this is a really key bottleneck that actually leads to intelligent behavior. And so that's the kind of research that this talk that I want to talk about, which we presented at Coral. And so it really started, my student Justin, he likes to go skiing a lot, and he's thinking, about his research. And then he took Bruno Olshausen's human vision class. And one day he's like, you know what, Angjoo, I want to make an eyeball. Because humans have eyeballs, and the way we perceive is very different from the way that we currently handle camera and image inputs in robots. So I think there's something about this. And then he spent like 3 months, I don't know how long actually, he was trying to do this for a while. He just one day made this robot. So this is like his little eyeball. It was a great mechanical engineering like exercise to learn how to make this. It actually can move pretty fast. And then we figured out, we were like, let's do something with this eyeball. And so what we ended up is this eyeball that will look at the places that you need to look to achieve a task. Okay, so now I'm going to show a video, and that's going to be from this eyeball's perspective, okay? So it goes like this. You instantiate an eyeball, it's looking around. Oh, and it needs to look for the towel. It's very excited about the fact that I found the towel. Now it's grabbing the towel, and now it's looking at now I found the bucket to put the towel in the bucket, which was the particular task in this case. So I will show you this video once again, but from the front on. So this is what you're seeing. So we mounted this little eyeball at the base of this arm. That's the view from the eyeball, and that's kind of how you can see it from the third person view now. It found the towel, it has to find the towel, and then put it into the bucket. And the bucket and the towel may be anywhere in the workspace. Okay, so this is kind of what we are talking about. But before we get there, let me take a step by step of why we're really trying to do this. Because Justin and I, and along with lots of my group, has been working on lots of really cool research in multi-view scene reconstruction. You know, like G-Splat Nerf Studio, and we really have such great representation to do this kind of thing right now. But this may not be always what you want, actually. And here is a test. Okay, I'm gonna show you the scene, and then you have to look for Waldo. Okay, so please look for Waldo. Where's Waldo? And then you should study this scene carefully, because later I'm gonna ask you questions about it. So, okay, I see some arm. Okay, yes, Waldo. You found that Waldo. Okay, great. Okay, so you found him, right? Easy enough, he's in this spot. Okay, so you take this video, and then you ask Claude, where's the Waldo? And Claude said, I can see your desk set up with some interesting items, but I don't spot Waldo in this image. And then starts listing all the other things in this image, which is great. But it doesn't see the Waldo. And why doesn't it see the Waldo? Maybe if you just train more with more images and more scale, it will eventually. But maybe not, because the reason why it can't see it is because these modern image architectures is trying to just throw in every single thing about this image into this magical latence. And from this latent, you're going to ask where the Waldo is. Okay? And this is gonna be a very challenging thing to do, because this single vector has to be an exhausting representation about the scene entirely. It has to compress everything about the world, like the semantic or the depth or boundaries or textures or action. That's not really how we think about the scenes, you know? You cannot answer all of these questions at once. And maybe you can, but then it's a very difficult problem to compress. And this is even more apparent if you're a robot, because here is like a 360 view of a scene, of a room, and you're like, grab me a Coke. Okay, now I have to go to let's see. Okay, maybe I'll go to the right because I see a fridge. Okay? But where's my laptop? Okay, that's right in front of you. Can you find my keys? I mean, all of these questions that you might ask a robot to do, you can't just, digest one big image. And this is because the pixels that we care about change based on the task. So what if vision models? So if, you want to look at this refrigerator for the Coke, but then the laptop and the dining table, you have to look at different areas in the scene. So what if vision models could actively select where they allocate their compute? To demonstrate this, here's a pop quiz. So do you know what was inside the bulldozer? Does anybody remember? You saw this scene earlier. I did this last time, and there was one person who actually said it, which was pretty cool. But if you paid attention, which you wouldn't have because I was asking you to look for the Waldo, you would notice that there is this little Miffy bunny in that bulldozer. So that's what it was. But you didn't see it because I think it's an example of how you're not really seeing everything at once. And this bias to ignore, actually, is a very nice one. We've seen it over and over again in our architectures like RCNNs. Even attention is this type of selectivity, learned selectivity. And so what is the selectivity for embodied vision? There's two. One is fixation, which is kind of like moving your neck to really only fixate on certain areas of the room. And the other type of selectivity happens actually inside your eye in foveation. So I asked ChatGPT to make this picture, and it doesn't really understand foveation, but it's okay. It's basically how the eyes have multiple resolutions. The distributions of your cells are really focused in the center, and the peripheral is not as much information. And here is a very famous paper that says that, humans actually look at wherever they're going to touch. So if you are about to, eat a toast, and then you're gonna first look at the thing before you actually do it. It's a form of planning. Okay, so there's this, okay, now I'm going to show you this video. And so the task, I'm gonna show you a video, and you have to count how many times people pass around the basketball or the ball. Okay, here. Okay, that's 1, 2. Okay, so please do it. Okay. Do we have a... Okay, how many passes did you count? 20. Okay. Now, did anybody see the gorilla? Did you see the gorilla? You saw the gorilla. Okay, so I didn't see the gorilla when I was first trying to do this, because I was very focused on counting. Yeah, so as you do this, there's a gorilla that passes by. But if you're really focused on counting the passes, you may not have even noticed. I didn't notice. And so that really is kind of talking about how extreme this foveation can be. Okay, and this fixation pattern varies widely based on the task. And but the most important part is that this behavior is never supervised. I mean, potentially we could supervise this, but you really want this to be an emergent thing. And how can we really emulate this with a robot? And that was our goal. And so in order to do this, we wanted to make it task-driven. So we gave it some tasks on the arm to do. This was like, picking up the towel. And then we also have this eye. And so the eye has 2 degrees of freedom, and with this global shutter camera, and then this stuck to, mounted on this ball. And then so here's the example that we were looking at in the beginning. And I can show it one more time. So it starts out, right? And when it first starts out, there's nothing in the scene. So it has to actually look right or left. It looks right, and it actually sees the bucket. And you're like, okay, but then I need to find the towel. And so that's why it looks left. And it really does get excited. I'll talk about why it does this thing. And then after the thing grabs, it goes over there. And this behavior of what to look is never supervised in our framework. And so how do we do this? And so the idea is that the eyeball is trained with RL, while the arm is trained with BC. And the reward for the RL agent is to successfully complete the BC, successfully follow the supervision. And so here's the detail. And so our physical eyeball has this high-speed camera gimbal, and it can actually do very quick motion as well as smooth pursuit. And so how are we going to train this gaze policy, right? So one thing we could do is to do something like BC, where we collect data with people's kind of fixation movement. Or we could also use ARIA glasses, and we seriously considered doing this and actually tried using it, which actually does a very good job doing this tracking. We wanted this to discover the strategies in which to watch. And the problem was that, like, if you had the gaze demos, there is no counterfactual of what would have happened if you looked on the other direction. And so that's why the real key challenge is to train this in a simulation. You really need to do tens of millions of environment steps. And you have to be able to generate counterfactual situations and learn from that. And so this is why you need a simulator. And in our solution, it's a cute solution, which is that you can actually do real to sim very easily with a 360 video. And so what we're going to do is take the same setup, but replace the eye with the 360 video, and then capture all of the BC data. Okay, so you can see the jello in the back where like the human teleoperator is manipulating the arm to collect the right behavior to do. And then later, the simulation, you can actually simulate counterfactuals in this scene, or it's basically almost lossless sim to real or real to sim, right? Because you can actually just crop and render certain areas. Okay. And so here's some captured 360 videos. And in order to simulate the eye, we also do a foveated multi-crop render. And I will get into more details about this. But let's look about how to really do the action. And the idea is to look to maximize the success on any task. The task in this particular situation is following the popular way of doing things in robotics is using behavior cloning. Could be anything else, actually. And the key idea is the eye is with RL. The rest of the body is BC, but really more about a task. Okay? And the thing is that the eye is the one that is supplying the images, and then the arm policy takes that image to execute. So the reason why this works is because if you actually give an image like this and say the task is to grasp a cup, there is no cup in the image. So then you don't really know which way to go. You could go left or right. So then you'll get this wrong 50% of the time. But if your eye looked at this scene, then you know that you should really go to the right, and you will get this almost all of the times. Okay? And so that is really how this works. And so the idea is that the eye model takes in the eye history, motion history, and then outputs an eye action. And that eye action gives images to the robot model, and the robot model outputs some action in a supervised learning manner. And if that predicted action is the same as ground truth, then you get high reward. And so you want to pick views that actually gives you information about how to solve the scene. Okay, so here are some examples. So in the beginning, this is kind of what the randomly initialized actions look like. Okay, and during the training, we also give 1 second of pause time for the eye to explore and make sense of the scene, and don't really start moving the arm. And then 7 million steps of PPO later, the policy starts to converge and starts to look at things. So we kind of saw this behavior. And so look into the more details about the architecture. We have an input where the input is an image as well as the gaze direction and the proprioception. And the output of the whole system is the delta gaze action. And the action chunk, as well as this eye critic, is for doing actor critic and PPO. So the point is that the gaze direction. So you have a eye transformer that keeps on taking eye action, eye history, and then outputs the eye direction. And the eye direction becomes this image tokens and then gets sent to the arm transformer. So one neat thing is that we actually did this foveated feature extraction. And there's a really nice reason to do the foveation. And it's really actually more of computational reasons. And we will show this. We take these center crops, and we do it like an image pyramid. And the nice thing is really, you reduce the amount of pixels by, order of magnitude by putting it into this multi-scale representation. And it's very computationally efficient. Without foveation, you need so much more tokens to actually digest this image, and it doesn't even fit in a 24 gigabyte GPU memory. Without the foveation, you really don't get enough resolution. It's only 448 by 448. In this case, we actually have 4 copies of 224 and 224, but you're actually having multi-scale information. Okay, so a really nice thing is, I have this really paper called scale invariant neural networks, which is that, you want to learn a kernel. Suppose you're looking for a ball and you have like a kernel for a ball, but that's for a specific scale. What if there are multiple scales of the ball happens at a different scale? Then you don't really want to actually have to relearn the same kernel for multiple things. And so that was kind of like the motivation for that paper. But the nice thing is, if you actually have foveation, this type of image scale invariance kind of comes across naturally. So take these two different scenes. So at the bottom, this object is closer to the camera, and at the end, it's further away. But you're actually going to have two scale inputs that look basically the same, right? And this actually gives you really nice robustness to out of distribution scale, which I will show later. One really neat things actually about the way we designed this is that every single pixel in this foveated image has a positional encoding, what the XY is. But that XY is actually relative to the eye, relative to this whole kind of multi-scale setup, not relative to each image. So so here is a good example. So this position, these places with the arrows actually have the same positional embedding because they correspond to the same place in the big picture. And so this allows the network to use positional encoding to share information across scales. And also the tokens are centered. That's another foveal bias. Okay, so we discretize our actions for the eye, for the ease of doing PPO. And the arm is doing action chunking, which is like a very popular paper in robotics. It's ACT. It's a very basic way of doing BC. We're not doing full attention across images because that would be too much. So we're actually only doing within image attention and not like image to image. And that would be really nice to do perhaps in the future for history. But we didn't do it for computational reasons because this actually had to run in real time. And so it runs in 60 FPS. Okay, there's history for the eye action. And the first thing actually we tried was to test out the eye with an RL objective. So we have this Boris bear, and we used clip, and we said brown stuffed bear to the clip. And we would give it high reward if the clip vector from one of the window had high similarity to the clip image. And we actually trained this on 5 minutes of videos captured using 360 like this. And then trained this. And this is kind of what it looks like. So this is a view from the eye. And you can see that it's actually learning to track the Boris. And in this case, the tracking objective comes from clip, but it's pretty good. It actually is quite snappy. And this is the example of this out of distribution experiment. So, okay, I'm going to redo this again. So this one on the left is using same amount of pixels, 448 by 448, but a uniform scale, trained on the same data. And on the right is with our foveated input. Then you can see as Justin walks back with this, quickly this goes out of distribution because it has never seen the bear so far away in that small size. But because of the scale invariance of this multi-scale representation, in one of them it has seen this small one, so it's a lot more robust. And I thought that was really a cool geometric inductive bias and a really nice feature. Okay, so that's another cool, interesting thing is about memory. So for example, if you kind of hid, then you do need memory to learn some kind of object permanence, that things come back. And so you've actually trained this without any memory. The moment the bear hides, the eye is like, oh, I don't know, what am I gonna do? And then like tries to look for it, and the gimbal is actually connected to a cable and it's not 360 for real, so then it kind of gets stuck. But if you give 1 second of context on its proprioception, then it does actually kind of hover a little bit and like waits for the bear to come back, which is quite cool. And yeah, memory is really another really interesting theme in all of this when you're doing online things. Okay, so let's do it on actual action. So that was all just tracking with clip. And so we defined some tasks that we collected a number of demonstrations using teleoperation. They're not really actually that crazy amount. And so here are some examples. So this is a task of e-stop. So the task is to go on top of this button, not to push the button, just to like follow it. And here is some results from the robot view. And this is the result from third-person view. Yeah, and then so they're kind of being mean to this robot, but the robot learns to kind of follow. Okay, again, it's another type of let's see if this video plays. It's another, yeah, even though they're same number of pixels, again, the multi-scale cropping makes it a lot easier to kind of fixate in the center. It's at least a lot more stable fixation. And it also helps ignore distractors. So if you actually show this yellow cup, the uniform one kind of can't decide which one is the right thing to go to. But with the foveation, it's a lot better at ignoring the thing in the peripheral. And we also do evaluate this, that the foveation actually helps the performance as well. Here's another task where you have to continuously servo the screwdriver to be perpendicular to this wood. And it does this. And it looks for it. It looks for the wood. And another thing is that you can actually work on a large workspace where the object is not initially visible, so you actually have to search. The most, I think, interesting example is this type of long horizon task where you have to find the towel and then pick it up. The really cute thing is that after we actually train this, now you can free drive the arm to actually go down on it. Then when you go down and grab the arm, it thinks, oh, I'm ready to actually look at the bucket. But then if you actually take it out, you're like, oh, I need to go and then grab the towel. And so it actually looks at the different things. And so this is a hand-eye coordination, actually, that is emergent behavior from our experiment. So I thought that was really cool. Here's another example just to show you that it also works when the bucket is on the left side. It's not always on the right side. And then you can move the bucket around as well. Okay, so yeah, and then you can also do a brush handoff. So if you look at the eyeball in the center of the image, you can see that it's actually looking at you because the task is for you to grasp it. You know, so it's like first it's looking at the brush, and now it's looking at the person. Now see the eyeball is like looking at the cameraman. Okay, so what about wrist cameras? Because that's kind of what robotics people are really into. And wrist cameras work really well, and that's actually because it does actually offer tool-centric fixation, right? Because it's like ImageNet. ImageNet is easy because the dog is always centered. And wrist cameras actually give you that as well. And eyeball is like that too. And that's like the pitch, which is that you can actually have the eyeball, and maybe you might not actually have to have the wrist ball in the future. Because these type of fixation narrows the visual distribution. Recognition is much easier when the object has been detected. Anyway, in this experiment, we did do the wrist camera baselines with also an external camera. With the wrist, obviously, it can do it if it's in the view, but if it's outside the view, it can't search. And the exo camera lacks precision because there's a lot of information to put into the network. So this is like the problem with the quad. Okay, so Yeah, we get this kind of like weird kind of oscillating action. And that is because we discretize the action parameterization and there's no incentive to stay static. And so it kind of like does this switching thing left and right. I think it's a matter of changing your action representation. If there's not enough data, it also learns to grasp without looking. And then if you add more training data or make your training harder so you actually have to look, then it will start looking. Which is kind of reasonable, right? If you know where it is, you actually don't need to even look. Yeah, there's like, there's data always has hands, and so the model naturally has this kind of affinity to hands. We only have a single camera, so it's hard to pour wine into a wine glass because you need a stereo for that. The eye can get stuck, and so there's a lot of things to kind of work on in this direction. But in the future, so we made this thing called iGym, which basically it's this 360 environment. So you can actually take a YouTube video, like a 360 YouTube video, and then make an iGym and actually, search for face using clip or feet. And then this actually kind of gives you like a policy that can search for things in 360 videos. Here's another like pre-training that we kind of try to explore, which is take random 360 images and then crop random places, and the task is to look for that area. This is actually pretty, and I think this could be a nice pre-training objective for these type of things that is enabled. Yeah, and of course, we really want to dig deeper into memory because in order to have interesting in-context learning capabilities, you actually have to have reasonable amount of history to adapt. So that's a real challenge also in Tutor, and I think this is a really exciting direction right now. Okay, here's some videos of a baby. So this is my baby, and when she could walk around, she's here in Hawaii. She's much bigger now. But this is when we took her to my office. And look at her. She's just like walking around because she's just like curious. There's no agenda. I mean, I guess I'm here, so she's trying to come to my location, but she's just kind of looking around. And so this type of, curiosity-driven type of task, I think is a really exciting thing to revisit now. And of course, one limitation is that right now it's only 3 degrees of freedom. And truly, it would be really good to do it in 60 OF, which does require an environment that you can actually do sim to real on it. But potentially, that could be possible with the reconstructed environments. Okay, all right, so what is the time situation? Oh, it's exactly the right time. Okay, so maybe this is just a quick teaser. So my lab is doing other robot stuff like video mimic, in which we actually use the images to teach reconstructed videos to teach robots how to walk around. But yeah, now the time, let's just summarize it. So it's a really exciting time to revisit active perception. In this particular case, we use task as a reward for the eye movement. You need a simulator. Here we use the 360 videos. And there's lots of tools like Visor. Have you used Visor? Yes, okay, Visor fans. If you have not used Visor, you should check it out because that's basically kind of how we do all of our research, and it's a 3D visualization tool. Of course, we have some cool news is Visor is now deeply integrated into robotics. So that's a Pyroki, our motion planning toolbox. That's another open source project. This is Isaac Gym. That is also another Isaac Gym, but you can actually do plot in Visor, so you can actually see your training. And then here is Mujoko. Visor actually runs directly on the Jian, and here is actually the visualization from that. You can also use it to, show all of your cool results, 3D results on your internet. And so, yes, so we have lots of cool tools, of course, with G-Spot and Nerf Studio. So that's what that was. And I want to say a big thank you to my group and collaborators without whom this is not possible. Okay, thank you.
Let's get started. So today I'm hoping to convince you that human data will be used as a foundation for robot learning. And for those of you who are familiar with robot learning, I think this is a viewpoint that many people can't get behind, but I'm going to convince you, if you're not from this background, that why this is a good idea, right? So the motivation for work is that most of the AI systems we see today are driven by human knowledge. At this point, a large part of human knowledge is captured by the internet, and the knowledge in turn gets basically downloaded to a gigantic internet.zip and put into large models like GPT, Gemini, and to basically serve the system we see today. The problem is that robots, transferring knowledge is very slow. You might have seen these kind of programming paths for robots, industrial robots specifically. So they're programming interfaces, but the sort of bits per second information flow is very, very little. And recently, the robotics community has rediscovered teleoperations as a way to transfer sensor motor knowledge from human to robots. For example, here we're seeing that people train a robot to do tabletop tasks or clean up a kitchen or a bathroom or do laundry, especially on the lower right-hand side. That was a very impressive demo of carrying the full sort of laundry tasks with the Pi robots. For those of you who are not familiar with this topic, I will quickly explain what teleoperation is. So, for example, in this case, Jay was controlling this robot was an iPhone, and in this case, what we're capturing essentially is what robot sees, is in this case, the camera stream, and how it should react. And through this pair of two data streams, we're able to train a policy that maps perception or pixels to actions. And very important thing is that we are essentially demonstrating our sensor motor knowledge through acting through the robot's body. So in this case, the knowledge being transferred is beyond just semantic level knowledge, but rather sensor motor knowledge that's largely missing from the internet. The problem is that teleoperation is still a really low bits per second way to transfer data, so it imposes a very tight bottleneck. And so for those of you who have done teleoperations, you know that's very unnatural, very intentional efforts, and of course you have to bring the robots around for whenever you want to collect the data. And I argue that it is very unlikely for us to reach data scale for other domains like vision and language if we rely on teleoperation alone. And the questions that our labs is trying to answer is how do we transfer sensory motor knowledge from human to robot at scale? Our research pitch is instead to learn from human experience data. And this data will be collected from humans with no robots involved, but containing sensory motor knowledge essential for policy learning and can be captured without intentional human efforts. This led to our first landmark results, EgoMimic, scaling imitation learning via egocentric video. And the core of this project is to capture embodied human data from egocentric view with wearable devices, and which means that we can collect this data anywhere. And unlike third-person views from the internet, this data captures how we naturally perceive the world from our eye at eye level. And specifically use the Project RA glasses to capture these data, which are capture essential information such as hand tracking and device poses that will be useful for robot decision making. And our work is about turning these raw data stream into embodied human data that can be treated as equals with robot data. So think about a spectrum where humans somewhere on that spectrum, but there are many other robot embodiment that's on the side. But the important thing is that we treat all of them as equal data sources. And we achieve this by bridging sensing, action, and kinematic gaps, and develop joint policy learning algorithms that can scale primarily with human data. So the more human data, the better performance. So one of the most important design decisions we made is to make our robot embodiment human-like, and that turned out to be a very important decision. And because back in let's say circa late 2023, there weren't that many options for human or robots, so we had to build our own lightweight lean human-like embodiments, so which are basically 2 arms with a pair of glasses, which turned out to be another important decision that we use the exact same cameras for both robot perception and human data capturing. First of all, it allowed us to mitigate any gaps between human and robot cameras, and second of all, we were able to match the sort of viewpoint between human and robot so that it minimizes the viewpoint gaps. One other interesting problem we had to deal with is that our head moves and robots' heads don't. For example, for this, the robot we have a fixed camera or fixed torso, and the actions or where the end effectors are based on a fixed reference frame. But so this way allows us to create this kind of smooth action trajectories. But for humans, we move around. We turn our heads to different directions to look at things, which means that the hands will be referenced to a moving camera frame, especially that you're wearing Aria, and that's what's tracking the hand. So which means that in order to make human hand motion more like a robot action, we need to turn them into a fixed, be able to track them in a fixed reference frame. And luckily, Aria gave us exactly that, which is the VIO or device pose from SLAM. And that allows us to basically back project future actions or future hand poses back to the same, to the original camera frame. And this was one of the key design decisions we made, which is to kind of do this post-stabilization. So in this case, you have these per frame hand track. And once you smooth them out by back projecting them to the same camera frame, this allows us to create these kind of future action trajectories that are used to train the policy model. So with aligned observation action space, we were able to design a very simple architecture that co-trains from human and robot data. And almost all of the network weights are shared among human and robots. So it's able to learn a shared representations that scales policy performance with human data. So we train our model on a variety of tasks and test them out. So in this case, this is a grocery bagging task. It's actually somewhat challenging because bags are slippery, so sometimes makes mistakes. For example, dropped here, I had to correct that mistake. And also trained the robots to fold shirts of different colors and sizes. And of course, we'll have to kind of make coffees for the graduate students. So we train the robots to do exactly that, not just espresso, but pull over, so which extra fancy. So the question, despite all of this nice results, the question we still want to answer is that does human data scale the robot performance? And on this case, we have a 2 axes. So this figure shows y-axis is the task performance, and y-axis is hour of data. And in this case, if you only train on robot data, which shows you collect 2 hours of teleoperation robot data, you have a mild scaling curve. But as soon as you add 1 hour of human data, you see this performance jump. I think we believe this is mostly because we can collect data a lot faster than robots. Like humans, our hands move a lot faster than teleoperation. So in this case, for certain tasks, we can collect 10 times as much data in a unit amount of time, which means that, and these are people who have spent a lot of time teleoperating robots, so are really, really good at teleoperation. So if it's for average people, you will have a lot lower rate than this. So you'll have an even bigger gap in human-robot data collection rate. We also wheeled our robots to different parts of the campus and show that it still works and it's robust. In this case, for example, for lower right corner, the graduate student kept on tossing more chip bags to the robot for it to handle, and is able to handle that correctly. So those are very exciting results. So that was our first sort of landmark results. But the question is, where do we go from here, right? So in this paper, what we've shown essentially is that we can scale robot performance, the success rate, with more human data added. But the underlying assumption we're making is that we have paired human and robot data. So we have the exact same set of, we have to collect both human and robot data for the exact same task, like folding clothes or doing grocery. And it would be really nice if we can just add human data before a completely new task and robot will be able to learn it. And this is what we call zero-shot transfer. So learning to solve tasks only seeing human data. And our first work, despite the success, was not able to do that. And we want to kind of understand why that's the case. Our hypothesis is that the reason that a model can do zero-shot transfer is because it has learned a generalizable domain invariant policy latent space. For example, if you have a batch of data, like raw observation data for folding shirts for both human and robot data, ideally, by co-training from these two sources, the model will be able to project them to this embodied invariant latent space that allows it to map it to an action, correct action, right? Both for either for human or robots. An exciting thing is that if you are able to do that, then let's say if you have a new batch of data from only human, right? Let's say fold shorts, then ideally, you should be able to project this back to the same space, and because this space is embodiment invariant, it should be able to also map to the correct action that allows the robot to fold shorts, or both shirts and shorts without any human data. Or any human data specifically for folding shorts. So that's the ideal picture we have in our mind. But in fact, what happens is that if you just do co-training, this is what you get, right? So our undergrad student, Ryan, who kind of led this project, really just kind of dug into this latent space from EgoMimic and realized that, it's actually not aligned. And the performance boost was something else. It's not because we have a very aligned space, but some different reason that we don't know of. But we do have a very strong hypothesis that better alignment will lead to better transfer, or specifically the sort of the prospect of enabling zero-shot transfer. So Ryan went on to kind of design a method to do this, and specifically what we did was a new method called EgoBridge, and it's based on a theorem. Set of works or method or a theorem based on optimal transport, or specifically joint optimal transport. So if you're not familiar with joint or optimal transport specifically, this is really measuring how much work or how much distribution gap there are between two distributions. And the idea for using that as a distribution alignment objective is that we can bring these two distributions together without compromising their own marginals. So let's say if you want to bring human-robot representation together, sometimes you will collapse into a distribution where it's optimal for neither, but optimal transport guarantees that you won't change the sort of the marginal, the individual distributions that kind of compromise the performance. So that was a sort of a new method we developed. I won't get into too much details of how exactly we did that, because there was a lot of design decisions. On a high level, what we're trying to do is to find a transport map with some cost function that transports human data, both the pair of latent observation and action, to robot data. So if we can minimize the cost, we find a sort of optimal transport map and then if you minimize this loss, it will align these things together. And there's some design decisions I won't get into, but a very nice thing is that this objective is actually very general. So you can add more cost functions, such as, let's say, language alignment, right? Let's say if a human and robots are doing the same thing semantically, they should be brought together. So that can act as a supervision for alignment. And another nice thing is that it's a plug-in extension to EgoMimic, so we can actually just say there are two loss functions inside of one. So this LOT is optimal transport loss. So it's still the exact same architecture with just one actual loss function and some special ways to handle sampling batch. Okay, so, and then we were able to see that with optimal transport or EgoBridge on the left, we were able to do line representation, learn a line representation, and if you can actually plot or actually visualize the data points at nearest neighbor points, they capture the exact same behavior between human and robots, which is exactly what we want. And quantitatively, we're able to show that EgoBridge outperformed all previous methods, including EgoMimic on these tasks we tested, like scoop coffee, drawer, or laundry, and it's able to enable stronger generalization to new objects. For for example, scooping coffee into a grinder on the left, generalizing to scooping coffee into like a new different can, or do this somewhere else, right? Like if you just move the robot somewhere else with a different table, different configuration, and still be able to do it. And one final results we were able to get was to learn new behaviors only shown in human data. And then that's what we'll consider as sort of a starting point of being able to learn to fold shorts from only paired data for learning folding shirts. Just spoiler, we weren't able to do the shorts one, but we were able to do this on a very, much simpler problem, which is, for example, in this case, we're training a robot to put things into these drawers. The purple region is covered by both human and robot data, and the red region is only covered by human data. So in this case, if a robot is able to generalize to that red region, we think it learns something useful just from human data, right? There's no paired data. We in fact were able to show that happened. It's with decent amount of success rate, and quantitatively only our method is able to do that. The rest of it have pretty much flat performance for generalization. Okay, that was EgoMimic, which was kind of direct extension to EgoBridge. That was extension to EgoMimic, and we actually had a parallel line of work called Mimic, which studied very similar problem, which is kind of how do we bring the representation together. And specifically what we're interested in is answering the question, does more human mimetic robotics hand, like dexterous hands, enable better transfer? And intuitively, the answer is yes, right? Because you have gripper versus hands. Hands should have enabled better transfer, but answer was actually more nuanced, and we had to actually develop a new method to enable this to happen. And the results was actually very counterintuitive. Is that the most important thing is not the kinematics, but the more the data distribution. So you can think of this as, let's say, your data distribution from robot and human needs to align. That's the only objective, right? The thing that doesn't really matter is the shape of your hands, and but because certain robot embodiments are more prone to, let's say, or easier to tell up with, or more natural to tell up with, that matches your human behavior, that allows more match distribution. So that was what was important. So if you're interested in this work, go search up Mimic. There was a Coral 25 paper that was just presented as an oral presentation. Okay, finally, I want to talk briefly about going beyond egocentric vision and tabletop manipulation towards tactile and full body motion. So far, we've only been talking about tabletop manipulation with egocentric vision. And one thing we did was to look at tactile, and specifically, this paper from Core 24 was about strapping a tactile sensor on your finger and record that tactile signal while tracking the position of the tactile sensor. And that was actually pretty successful. We were able to train policy from these kind of data and transfer that to robots. But because these kind of tasks are more difficult than just pick and place, insertion are a lot more complex in terms of you have to correct mistakes, these kind of subtle mistakes. So in this case, we had to do some RL fine-tuning based on the human trained policy, policy trained on human data. But that policy was a good starting point to initialize our training to, so that it can converge a lot faster than, let's say, training from scratch. Once the model is trained, we were able to deploy this on a variety of situations that kind of works on, let's say, different orientations of insertion, different materials, and different tasks, like lower right-hand side, where you have to screw the, kind of do the screwing the screw inside the slot. In the future, we're hoping to continue to make these devices. We're testing different kind of tactile devices to measure human. In this case, I think obviously this is not an ideal tactile sensor, and we're hoping to see more portable sensors be invented. And finally, my personal favorite topics go beyond tabletop manipulation towards mobile manipulation. Many of you probably have seen this mobile Aloha, very impressive capability. It's partially kind of reason that why robot learning is so hot today, but it's painfully slow, right? As you can see, the lower left-hand side, this is 10 sped up video. Especially the mobile tasks are typically long horizon, which is extra painful to collect. You don't want to be the person who collects this kind of data. And on the other hand, human data is almost trivial to collect. We do mobile manipulation data. We don't think about when we move our legs or move our hands or together, right? So, and one exciting thing is devices such as Project Aria captures more than just egocentric videos. We have the full body motion being captured. For example, we can see the left-hand side, the person's moving, right? You can see from the 3D world that where the hands is going to be, where they're seeing. So that pretty much captures our mobile manipulation data. Barring that we don't reconstruct the legs yet, we're working on that, but full body manipulation, the basis is there. So can we learn mobile manipulation from human data? The answer is yes, but we still need to borrow some static robot data. In this case, we don't have to move the robot around, but only tell up a robot to do the manipulation side of part of the for the task. And this is led by my student, Lawrence. So how we did this is, again, use Project RA glasses, and the data collection looks something like this, where the person has to kind of just do the manipulation with his hand and move around. There's not much specific instruction other than that. Keep your hand in a view. Don't move your heads freely. So there's some decent amount of instruction. I can talk about how to relax that assumption. But then we'll also collect a static robot data without moving the robot around. And with these two sources of data, we train the model very similar to the model I showed you before in EgoMimic and EgoBridge. And in this case, we have the special end effector head and navigation head that separately controls the upper body and lower body. And we have a face head that switches between the two modes. And it's necessary because of certain technical reason. I would love to discuss in details after the talk. And on the right-hand side, you show this exact same system, but we put a kind of differential drive robot wheel base on there so it can move around. And that creates some challenges because humans move omnidirectionally, right? Differential drive is that you can turn, you can do like Ackermann maneuver, but you cannot move on all directions. But humans can. So we have to retarget human motion to the robot motion. In this case, you can see that human motion looks like this. You cannot mimic that with robots, but with retargeting, you can see that there's a more smooth orientation curve, orientation trajectory that allows it to be retargeted to a differential drive base. So with many other things we've done, we were able to put together a system that solved very challenging problems. For example, in this case, we're able to solve this kind of serving breakfast task that picks up croissant and serve on the table. And another interesting task is serve wine. In this case, it needs to actually navigate to a person, and the person can be anywhere in like a workspace. So the robot is able to kind of adapt to the changes. And because we actually show that we don't need mobile data, so you can actually just collect your mobile data for human anywhere, and that policy should be able to generalize to that new environment, as long as your the sort of the manipulation side of this is robust. So in this case, we're able to train robots to generalize to a completely different use space for the same task. And finally, we train our robots to do this grocery shopping task where it has to pick up 2 chip bags, and a bigger one was both of this gripper and somewhat skillfully pick up this basket or shopping bag and move that or give this to a person. So that was a fairly long horizon task. And comparing that with mobile Aloha, we were able to see that our method performs a lot better. So the final success rate we were able to achieve more than 50%, while per stage success rate, you can see that kind of mobile Aloha drops over time, over the course of the task, and eventually it was not able to complete any task. So that was that was a very good signal for leveraging human data. And one final thing is that we see again a very exciting scaling trends. Was more human data added, you get better performance, and this was a very clean scaling curve with kind of statistical significance where we did 0.05 testing. So it was actually significant. So, and we were able to reproduce that on a variety of tests. So that was pretty exciting. So finally, to conclude my talk, I want to talk about some open questions that are on the top of my mind. So I categorize them to 3 categories: hardware systems, data and algorithms, and research community. So on the hardware and system side, the thing that I'm very curious about is how to capture human experience and context. And my claim is that first-person videos is not your sensor motor experience, and it's also not your decision-making context. In this case, for example, for sensing, we're still lacking, right? Obviously, we don't have robust sensors for tactile yet. We've seen some initial kind of promising trends. For example, Aria Gen 2 is able to capture much bigger field of view for camera for vision, and is able to measure things like heart rate. And this morning, some of you probably saw the live demo of Foundation Stereo, which gives us a stereo sensing, like depth sensing, which is quite exciting. But for tactile side, it's still quite lacking. So we're hoping to see more ways to measure human or sensorize human to however we can. So, so the things that informs the robot how human made that decision. And another claim is that the context that human use to make decisions is also not just instantaneous sensory experience. It's the sort of the past working memory or the knowledge, right? In this case, let's say if a chef is trying to prepare a dish, the reason that's this person is able to turn to the data counter, take the ingredient, dump it into the pan is because they remember the fact that the ingredient was prepared a few minutes ago. That was a context from a few minutes ago. And there's also the fact that they were able to adjust heats constantly to cook the perfect dish perfectly is because they've gone through years of training. All of this are the reasons that the person did a specific action, right? Tuning the knob and everything. And be able to assimilating that knowledge into a policy model is still very much an open problem. The second category of problem is data algorithms. And so I have 2 firm beliefs that the first one is human data is the most universal and scalable data source out of all embodiments. The second one is that more human-like robots will make human data more useful for robot learning in the future. So if you believe in that, you probably have this picture in mind, which is that we have a huge amount of human data with some amount of embodiment-specific data. And the question that's not clear is what roles should human and robot data play. And so one kind of pictures you might have is this kind of famous data pyramid from my colleague Angjoo, who kind of popularized this picture of like you have to have a scalative data source be the foundation for training a model, and you fine tune that with a small amount of, let's say, robot data that's more expensive. But I would argue that it's just as likely that we have this flipped pyramid where the robot data is the foundation, where you train a policy that's good enough so that can learn to do this basic primitives like pick and place and insertion that allows it to make good use of human data on the top. So both of these pictures are equally likely. You will actually build different models and have different hypotheses and probably write different papers based on the pictures I have in mind. I'm not favoring one or the other, but I'm just pointing out that they're both equally likely, and I want to see more exploration from both sides. And finally, I want to talk a bit about how we drive the collective progress of a research community. For robot learning, we have made tremendous progress through things like OpenX embodiment, Android. And for egocentric perception, we have Ego 4D, Apple Kitchen, and more recently, EgoDex, which focus on more manipulation data. But if we had learned anything from a few years of data-driven or data-centric robotics, is that data set alone is not going to solve the problem. We need a continuous cycle of data to algorithms to evaluation, especially on-robot evaluation that tells us what data is useful so that we can collect more of that. And at the same time, I'm hopeful this is going to work for learning from human data is because, again, we can agree on that there's a single most scalable data source. We can all contribute to this data source. And along with a few academic groups and industry partners, we're currently developing some standard infrastructure for this whole cycle. And the hope is that this would potentially enable the community to make things more comparable and accumulate more and more insights and useful human data along the way. I'm hoping to be able to share this very soon in the next few months, so stay tuned. And that was it. That's this talk. These are all the papers I mentioned. There are a few more on my lab's websites, and here are my sponsors. And thank you for being here.
So again, my name is Lingni. I'm a research scientist from the Siyu team. So today, actually, I want to talk about the Nymeria++, which is an upgrade to our previous release, the Nymeria dataset that we designed to empower human motion research in an even better way. So for people who are not familiar with what Nymeria dataset is, I want to give you a brief recap. So this is basically a massive collection of human motion in the wild that the team released the data at the ECCV 2024. The data was actually recorded with multiple project area Jian device and Jian alike wristband and motion capture suit. They are all time-aligned and spatially localized in one metric 3D world. And the data is annotated with ground truth, body motion, the human written narrations. As of today, the dataset is still the largest human motion in the wild, and is also the largest collection of human motion with natural descriptions. So this video is actually here to help you visualize the quantity and diversity of the data, where we randomly sample 100 snippets from the Nymeria dataset and show the motions here. Just to summarize, the dataset has these key statistics. And as I mentioned before, this dataset is fully released last year from ECCV 2024. And if you scan the QR code, they will bring you to the website where you can download the data, the code, the paper, or just simply visualize the data online or filter the sequences or modalities as needed by your research. Now, before diving into the details of why we upgrade the initial Nymeria dataset, let me first mention a few research cases that are uniquely empowered by the data. The first one is the algorithm that we developed for tracking egocentric body motions from a single pair of smart glasses. So this initially is a very challenging problem because from the form factor of smart glasses, even with multiple cameras, they hardly provide any self-observations. So traditionally, in order to solve this problem of ego motion tracking, people typically have to wear a lot of motion sensors on their bodies in order to estimate their body pose. And this is changed by using the datasets where we actually show, given a large quantity of data, we were able to train a machine learning algorithms to infer the full body motion, and we named the algorithm HMD2. So at its core, this is a diffusion algorithm that generates body motions conditioned on the headset trajectory, the hand tracking, the image embeddings, and the surrounding point cloud. And with this demo, we show the results of tracking the full body motion from a single pair of Aria Gen 1 device. And again, if you pay attention to the egocentric videos, you will see how little we capture the self-body motion, and yet the model is able to produce very reasonable motion. And because it's a diffusion model, so we're able to actually explain the ambiguous motion state by a probability distribution. So what we're doing here is to visualize the model by randomly sample it 10 times and overlay the prediction. And you can see the prediction is actually pretty tight when the hand appears in the view. That's where the distribution gets collapsed. But when the hand moves outside the field of view, the model is also able to give you a very diverse and reasonable predictions. Now, with the move on to the second study case, where we actually show even more powerful modeling techniques that we explore to build generic foundations for understanding egocentric body motion, which is we call the algorithm EgoVLA. So this algorithm is actually designed with 3 principles. They are, the first principle is we want to explore the body motion as language, such that we can harvest the powerful tool of large language models. Second, we actually also want to use a generative modeling technique so we can still sample the distribution to represent the ambiguous motion state. And third, we want to model the joint distributions of all the modalities, such as the body motions, the language descriptions, as well as the multiple sensor measurement. By doing that, we can open the door for a unified framework to achieve multiple tasking by marginalize the joint distributions later. And so with this algorithm, we can achieve multiple motion tasks. For example, an easy one is to condition the headset and the wristband trajectories to output the full body motion. And this is a relatively easy task, but still with EgoOM, we are able to show that our algorithm is able to give a more accurate and stable predictions, especially when we're looking at some challenging cases where the lower body is actually not observed. Now we also show we can use the algorithm to do even more challenging tasks, such as just from one single point of smart glasses to predict the full body motion. And when we compare the algorithm with the state of the art, we observe our algorithm is typically give much more accurate pose in general. It also gives much more energetic hand motions in many cases. Now, the most challenging task our algorithm is able to do is to jointly predict both the language descriptions of in-context motion as well as the parametric motion models. And with this task, we actually don't even see any existing algorithms that is able to do this, partially because lack of the data. So what you're seeing here is the output from our model where you can see the motion as well as the predicted in-context language. And often we observe that the language is very detailed. It's not only described how the person is moving the body, but also describing where the person is looking at, how they're interacting with the environment, as well as where the person is. Now, the third study case I want to show here is actually move beyond the egocentric body tracking, but into the exocentric body motion tracking. You might think that people have been studying this problem for decades and it must be solved. But actually, it's not. If you take a closer look, you will notice that most of the existing algorithms are actually focusing on either single view videos, which leads to state scale ambiguity, or they only allow the cameras to be static or move slowly or very slightly. And none of these is holding true when you put the smart glasses on your head, where the camera movement is very drastic. And so in order to solve this problem, we actually focus on developing solutions that will lift the moving people into the 3D space, which is spatially anchored in the metric 3D world. And in this video, it's showing our early experiment where you can see the person is wearing the Aria Gen 2 device, and we were able to track almost every single person that appears in a wide field view of the Aria Gen 2 device. It almost feels like you have an invisible eyes behind your head. So with this algorithm, we're actively developing it, and please stay tuned for the more technical details to come out. We also noticed that in addition to the research development by our own team, the dataset has been gaining quite some attention from the academia research communities. Here is just to list a couple of algorithms and recent publications, which their solutions are uniquely enabled by the dataset. Now, I want to actually switch gear to give you more updates on what has been upgraded with the Nymeria++ dataset. So before I give the details, I want to show you this teaser videos that in order to give you a good understanding of what Nymeria++ actually can provide. As you see the video, you will notice there's much more things that is going on. There's very accurate body motions, as well as bounding boxes seem to appear in the view. So let me break it down into the three major axes and describe each of these updates. On the first axis, we actually optimize the human motion and the shape. So in the previous previous release, we actually almost solely rely on accents to provide the ground truth body motion. The only modification we did is to align the motion into the 3D metric world of the ARIA device. Now, this leaves a lot of motion artifacts that remain undressed, such as the foot sliding, the inaccurate end effectors, especially with the hand motion. And in previous release, we'll also use some simple algorithms to retarget the accent's motion into a human parametric model for visualization purposes without too much care. Now, in Nymeria++, we actually address all of these limitations by improved upper body motion using the wristband accurate 3D tracking. We also reduced the foot sliding by using the velocities and the foot contact. We did a very careful optimization to retarget accent's kinematic motion into Meta's latest human motion model that is shown on the right. We also are retargeting these parametric motions into the simple format such that the dataset can be combined with the other simple format motion dataset out there. Now, the second upgrade we did is to add 3D bounding box annotations into all of the indoor collections of the Nymeria dataset. And these 3D bounding boxes include both objects as well as structures. So you end up with bounding boxes for the chairs, tables, these common objects, as well as the common structures such as walls, floors, even staircases, and windows. Now, these annotations is motivated by the principle that we believe human motion is a function of the environment, and this environment context provides a great constraints of a lot of human motion understanding algorithms. Now, in this video, we actually shows just the 47 unique Airbnb locations with the fly-through of the bounding boxes. If we further project these bounding boxes into the RGB view of ARIA Gen 1 device, you will see how accurate and how dense these annotations are. And just to provide some simple statistics, all of these annotations are derived from the 47 Airbnb base maps. However, we do fine touch every single individual recordings to remove objects that have been moved around. Or add objects that are not being observed in previous recordings. In total, we have defined 19 predefined semantic classes, which leads to about 12,000 semantic objects being annotated. We also add one freeform category, which basically include anything that you typically see at home. And this leads to another approximately 10,000 unique instances being annotated. The third upgrade we did for our dataset is to release more data and more modalities. And this includes 50 hours of additional data that we cleaned up after the first release. We're also including all the base map recordings. These are very good recordings to run algorithms of static reconstructions. We are also including approximately 600 hours of these wristband videos. In previous talks, you probably already get the ideas why these wristband videos can be extremely useful for robotic learning tasks. In addition, we are including 600 hours of audios coming from ARIA recordings, and these are typical recordings record interesting interactions between the participants and the moderators and their conversations. Last, we are also evaluating if we can further include dense object reconstructions coming from the latest algorithm called ShapeR. An example of the ShapeR reconstruction is showing you here, which includes instance-wise very accurate object reconstruction that further enrich a simple 3D bounding box annotations. Now, to conclude the talk, I'd like to show you this video. This video is actually not the Nymeria dataset, but a lot of the algorithm that builds into this inference is actually learned from using the Nymeria dataset, for example, the egocentric body pose and the exocentric human motion running in real time. And with this video, I'm hoping to inspire people who are interested in using the data to do different type of researches of contextual AI. With that, I'll conclude the talk. And here I would like to mention all of these amazing people who put a tremendous effort into making all of this possible.
Today, I'm going to share our work, EgoVLA, Learning Vision Language Action Model from the Egocentric Human Videos, represents our exploration into building generous model for textual manipulation using the diverse egocentric human videos. I'd like to start with our motivation about utilizing the human data for manipulation. First, considering the human as embodiment, we get 8 billion people around the world across diverse environments. And this naturally provides potential diverse data for manipulation. Previous work utilizes internet-scale data for some kind of a pre-training without explicitly modeling the manipulation skills. Here, we explicitly model the manipulation skill in those videos. Second, the humanoid robot is reasonably close with human, so they share the similar egocentric viewpoint and also the similar morphology. Third, when we worked with like the tally operation and imitation learning, then we realized how the current robot data, especially the DEX hand data, are quite close to the human data. So it's just a few transformation and retargeting away in between these two formats of data. And as for how we utilize this human data for the manipulation, is we first train our model on the human egocentric data to obtain the basic understanding of the egocentric view observation and the human hand manipulation prior. We then fine-tune our model on the robot demonstration to finish the specific downstream tasks. In the EgoVLA, we use the existing video dataset, HI40, HoloSys, Hot3D, and Tuckle, and for their manipulation heavy setup. To the right is our data distribution after sampling, and since there are more and more data coming into the egocentric data, and we are expecting this to grow. And here's a task distribution for the HI40, HoloSys, and Tuckle datasets, and we can find that this human dataset covers a reasonable range of the diverse tasks. To utilize the existing knowledge in the visual perception and language modeling, we built our generalist model EgoVLA upon the existing VLM. We fine-tuned the EgoVLA 2B to predict the human hand trajectory in the egocentric video frames, specifically the wrist pose and the hand pose in the egocentric frame. For the hand pose, we use the mono hands to represent and model the human hand behavior to further utilize the hand pose prior about the human manipulations. And later, we further fine-tune the model on a small set of the robot demonstration for the downstream task. And our input for our EgoVLA model is the multiple frames of the visual observation in the past, as well as the language description and the current hand states. The loss we use to train our model is the regression loss with action chunking, and we predict the future action for the next seconds in the 30 Hz. By doing so, our model learned to model the human behavior. Though we only visualize the wrist pose here, we also model the hand pose in our model, and the red lines here are the ground truths, and the green lines are the predicted hand trajectories. In this slide, we show our model predicting the hand trajectory for opening, closing doors, and the pick and place and pulling the waters. We also visualize whether our model could follow different language instruction. Here for the first row is the original data, aka the image and the language instruction pairs in the test sets. We replace the language instruction while keep the original visual observation, and we found that the predicted trajectory changed to follow the new language instructions. For the first column, we found the predicted trajectory is now pointing towards the door of the safe, and for the second column, the predicted trajectory is now pointing to the table instead of into the door. To fine-tune our model on the robot data, we need to convert the robot actions to the human actions, and during deployment, we then convert it back to the robot formats. The conversion is actually just a few transformations. We convert our robot demonstration into the human format, which our EgoVLA is trained on, in 2 steps. We first transform the robot wrist pose to the human wrist pose frame because they are defined in a little bit different coordinates. We then retargeted the robot hands and the key points to the human hand pose, which is formalized by the mono hand parameterizations. And then we can fine-tune our EgoVLA on this robot data. And during deployment, we just do the other way around. Transform the predicted human hand pose to the robot coordinate system, and then retarget the predicted human hand motion into the robot hands. And then we're ready to go to deploy on the robots. with the purpose of the reproducible evaluation of bimanual dextro manipulation, we build a simulation tasks which include 12 tasks with diverse visual backgrounds and fine-tune our model on these robot tasks. Here are some visualization of the tasks included in our benchmarks. It includes 7 short horizon tasks and 5 long horizon tasks. Here's our robot performing different tasks in the simulation, ranging from short horizon tasks and peak place and to some below longer horizon tasks. As in the human trajectory prediction, we visualize a predicted future and future end effector trajectory as green dot lines. Note, due to the transformation between the robot hands and human hands definition, the end effector dot is not exactly on the wrist, but it's a little bit off. And our model is also able to perform longer horizon tasks, such as inserting, unloading cans, and sorting cans, which requires multiple rounds of pick and place. And all these tasks are performed by the single generalist model. We compare our EgoVLA against 2 baselines. One is the EgoVLA no pre-trained baseline, which fine-tunes the pre-trained VLM on the directly on the robot demonstration without human video pre-training, and ACT, which trains the separate specialist transformer for each task individually. We compare the model performance under 2 settings. One is the scene visual configuration, where the visual backgrounds are identical to those environments where we collect the data in the training, and also the unseen visual configurations, where the visual background are entirely novel. We first evaluate our model in the scene visual configuration, as shown in the left table. As shown, the EgoVLA consistently outperforming the no pre-trained baseline across both the short and long horizon tasks. Gains are especially higher on the task requiring the fine-grained manipulations. More detailed per task comparison can be found in our paper. And the performance gap between the EgoVLA and the EgoVLA no pre-train is even larger for the longer horizon task, achieving approximately 20% higher success rate, showing the benefits of the human pre-train. Compared with the specialist baselines, the generalist model, EgoVLA and EgoVLA no pre-train perform substantially better on both the short horizon and long horizon tasks. As shown in the right table, EgoVLA maintains strong generalization in the short horizon task on the unseen visual backgrounds, with only a minor drop in the mean success rate, whereas the no pre-train baseline shows a 23% declines. Even though the human video boosts the performance in the robot manipulation, we found that with the same amount of the human data but less robot data, the performance of our models drops a lot. This indicates that we still need a reasonable amount of the robot data to learn the interaction with the environment and get familiar with the exact embodiment for the specific tasks. To further see the impact of the pre-trained data composition, we pre-trained EgoVLA using different data mixtures. As shown here, the results shows that increasing the scale and the diversity of the human data consistently improves the downstream performance, with both the average success rate and the progress rates increasing across tasks. And we also shows that our model with good spatial generalization across the different object pose in the test setting. For a short summary, would be like the human video enables better generalization in the novel setting, and also the human video could boost the robot scale learning. And more results and the details and code can be found on our websites. Thank you.
Okay, hello everyone, I'm Jian, and I'm currently a research scientist at Meta-Reality Lab. Today I will discuss my recent works about the egocentric human motion capture from multi-modal inputs. Over the past years, we've seen a wave of new wearable devices, from the Meta Quest 3 to Ray-Ban smart glasses and Ray-Ban display. These devices pair lightweight form factors with on-device cameras, displays, and compute, enabling everything from immersive VR to everyday AR experiences. These wearable devices support a range of everyday applications. from VR gaming, telepresence, and personal digital assistants. All of them rely on precise low-latency motion tracking, for example, to animate the game character or drive a photorealistic 3D avatar for interactive co-presence in VR. Equally critical is the semantic understanding of the movements, which enables the everyday assistants to recognize hand actions and infer timing and motion intent in the tasks like cooking. Modern wearable devices can give us very rich multimodal inputs for the motion capture and understanding task. For example, the pose and vision from the cameras, the IMUs for the human body dynamics, and the microphone for the audio clues, and even the EMG for the muscle intent. Each sensor is good at something different, and each sensor has its own noise, drift, latency, and occlusion issues. The research challenge is to fuse these heterogeneous signals so they complement one another and produce accurate, stable, real-time egocentric motion capture and understanding in the wild. In the next part, I will introduce my recent papers in the CVPR 2025, where we explore multimodal sensor fusion to push motion capture and understanding forward. The first paper I would like to discuss is the EgoVLA, Egocentric Human Motion Capture and Understanding from Multimodal Inputs, which is on CVPR 2025. The task of this work is try to serve as a co-pilot for the everyday life. In the everyday life, we might wear a smart glass with egocentric camera. We also might have the IMUs that might come from the smartwatch and cell phones. From these sensor inputs, we seek to enable the capture and understanding of the human motion for a number of downstream applications, especially for the telepresence and copilot work. To reach this task, we present EgoVLA. This is a system that can simultaneously track the human motion and generate human motion descriptions from arbitrary combinations of multimodal inputs, including the image, the text description from the audio, and the IMUs. In terms of the methods, our framework consists of a motion capture module, a motion description generation module, and a feedback loop, where the generated descriptions can help to refine the motion predictions. The first key component of our method is a training of EgoVLA to learn discrete latent space, where we call the motion token space. This process involves encoding the human motion into a compact representation where different body parts are encoded separately. The advantage of this approach is that it can enable flexible motion reconstruction even with sparse IMU inputs. By mapping motion data into a part-specific token space, we ensure that our system can operate reliably across different sensor configurations. Once we have learned the motion representation, the next step is to train the multimodal encoder that takes input from different modalities, such as IMUs, egocentric images, and motion descriptions, and to predict the human motion. For example, an egocentric image might provide visual clues about the surrounding environment, while the IMU captures precise limb movements. By integrating these signals, the encoder improves motion prediction accuracy even in cases where some inputs are missing or unreliable. After predicting an initial motion sequence, we apply test time optimization to further refine the results. Another key innovation in the EgoVLA is the use of fine-tuned large language model to generate the human motion descriptions. By training the LLM on multimodal data, including the egocentric images and the human motion tokens, we can produce detailed and natural language descriptions. So something special here is that we find that the generated motion descriptions are not just outputs. They can also serve as the inputs. They can also help to refine the motion capture accuracy. If the motion description is not provided as a motion capture inputs, we can feed these descriptions back into the motion model and further improve the human motion predictions over time. Now, here I show our results. The EgoVLA achieves state-of-the-art performance in egocentric motion capture and understanding from arbitrary combination of multimodal inputs, including the IMU signals, images, and text. We can see it can give very smooth motion and plausible text descriptions of the motion from any combination of these inputs. Our experiments show that it can outperform existing models in egocentric motion capture and human motion description generation across multiple evaluation metrics. This shows the effectiveness in diverse real-world settings. Apart from that, our model can support multi-round conversations, allowing users to interact with the system. This can enable the enhance the usability of the Ego4O for applications such as virtual assistants. Another important aspect of Ego4O is can generalize to unseen data. Even when tested on out-of-distribution scenarios, our framework is able to generate plausible motions and plausible text descriptions. So one problem is of the current Ego4O is that it only supports the images as the inputs. So I think, but for this, I think it will be very easy to expand to the multiple images, even the video as the input. Next, I will discuss the second paper called Frame, Floor-Aligned Representation for Avatar Motion for Egocentric Video. So this paper mainly aims at to capture the egocentric human motion, 3D human motion, in a real-time way. The task of this paper is to explore how to combine the VR head 6DoF tracking with the downwards-looking stereo egocentric camera inputs and to enable as accurate as possible human motion capture. Especially, we need to get very good results for the lower body region. In order to solve this issue, we firstly created a device that combines a Quest 3 headset with a down-facing fisheye camera. And we further connect them to a Raspberry Pi board and stream the data with it. And with this device, we collect relatively large-scale data. So it's like 8 hours. It's not very large scale, but it's quite large scale in the egocentric area. And we use it for training the multi-modal framework that combines the head 6DoF tracking and egocentric images. Considering the method, in the first step, we predict the egocentric 3D body poses separately from the left and right cameras. We transform these predictions using a 6DoF tracking data from the VR headset, moving them into a global frame of reference aligned with the floor. After that, we feed the sequence of predictions into a transformer network to obtain a refined version of the human motion. In this process, the coordinate system we use helped a lot in the process of merging the left and right poses. Because of the self-occlusion issue, for a lot of times, the left and right poses estimated from egocentric cameras are not very accurate. But if we could be able to align it with the 6DoF trackings of the head, and so this enables the network to understand where the feet is, where the floor is, and how the feet is moving on the ground. So in this way, it can help a lot in the processing of merging the left and right poses. So this system makes it very easy for the transformer network to fix a lot of lower body issues. So you will not be able to see any inconsistencies like the floating the feet or the floor penetration anymore. So here is our results. So from the trackings and from the down-facing cameras, we can see that we can predict very accurate and very smooth and no penetration, no floating issues especially for lower body. So this is very challenging for all of these other egocentric motion capture systems. So this is another example for the very challenging poses. So we can see here we can even do the push-ups. And yeah, so this is very challenging for previous results. Yeah. Looking ahead, one of the targets we can work on in the future is the egocentric foundation model. So first, I think this model should effectively utilize multi-modal inputs. Second, it should handle multi-modal downstream tasks simultaneously. So for this goal, one thing we need to do is to get some sort of data sets that contain such kind of multi-modal signals. So one of the works we're currently working on is to create a multi-modal data sets which contains very rich labels, especially the labels related to the 3D information and geometries, including the 6DoF head trackers, IMUs are separated on 5 parts of the body, and the egocentric cameras, which contains forward-facing camera and downward-facing cameras, and scene geometries, and even the foot contact losses. So we have some sort of insoles on the feet, so we can, whenever the feet is touching the ground, we can estimate the forces on the feet. So on the left, we can show some very simple illustration of this information we have obtained, and we are planning to use this data for a lot of tasks in the future. So another future direction is to use the human motion to drive the virtual avatar for the human telepresence. Following our previous ego avatar work, which used a single egocentric camera input to drive a 3D Gaussian-based human avatar, future research could explore dynamic avatar relighting and methods to minimize the input requirements. Yeah, so in conclusion, today I present 2 recent papers, the egocentric motion capture and our understanding from multi-modal inputs. So I also outline several future directions, and thank you very much for your attention.
All right, cool. Thank you. My name is Boxiao, and I recently graduated with my PhD from Stanford. So I'm now a researcher at Luma AI, working on multi-modal models. So this work was done during my PhD at Stanford with Adam Harley, Karen Liu, and Liu Kips. And it's called Real-World Humanoid Egocentric Navigation. If you're interested in learning more about our work, it's also going to be on Thursday afternoon at the poster session. So in this project, we asked ourselves the question, how far are humanoid robots from safely navigating in the real world? So we look at these prior works in visual navigation. First category is vision language navigation. And these works generally work by specifying a goal, either in terms of natural language or image. And then it's going to plan a long-term path leading from the current location to the target. However, these works generally assume a static simulated environment, which is, of course, not the case in everyday scenarios. And second category, which is called social navigation, which does short-term path plannings. And in the dynamic environments, normally there's 1 or 2 people in front of the robot. But these works are developed for navigation robots only, which will have a very different morphology and action and data distribution from humanoids. And lastly, there is more recent work on human-centric navigation, which also does short-term path plannings, and they're designed for humans specifically, but they also assume static environments. So another aspect that is missing in prior works is this behavior that we call human-like information gathering. So as humans, we would constantly gather necessary information relevant to our tasks. For example, before we cross the streets, we would look aside to the side of the streets to check any incoming traffic. And this is executed through the head turning events. And we would like our robots to learn these behaviors as well. So our contributions in this paper are as follows. We make steps towards a real-world deployable humanoid egocentric navigation policy by first, considering both the static and dynamic obstacles, and secondly, predicting head rotations as well as the translations to learn the human-like information gathering behaviors that we just said. And lastly, we propose a data collection pipeline that uses only a pair of Aria glasses, thus it's very easily scalable. So let's start from the problem formulation. On the input side, we're given a post-egocentric RGB video, which are shown through the black camera frustums here. And our goal is to predict a set of future 6D head poses, shown as the green frustums here. So a bit more formally, oh, sorry, so you're taking a picture, yeah. Sure. So a bit more formally, on the input side, we have a history of 6D head poses, and each head pose consists of a translation and a rotation component. And we also have an egocentric video of the same length. And for output, we want to predict the head poses in the same parameterization as the input. So here is our method. On the input side, we're given an egocentric video. We first apply a pre-trained dyno feature encoder on every frame of the video to get a set of 2D feature frames. And these are supposed to encode the semantic information, for example, the road structures. And we also have the camera poses accompanying the frames. And we want to lift these features up to 3D to give our model a more explicit notion of the geometry in the surrounding environment. So we do this with a strategy called parameter-free unprojection. So this basically gives the same features to all the points along each camera ray. And then we merge these features temporally through temporal average pooling. And this gives us one single 3D dino feature volume, which is here, this one. And next up, we project this feature down back to 2D again, because we are primarily concerned with the task of navigation, and this task requires information mostly in the bird's eye view. So this also gives us another benefit that we can perform a large amount of computation in the 2D space instead of 3D. And this is a lot more cost efficient. So we project the features down to 2D through NMLP. And lastly, the bulk of the computation actually happens in the 2D space, which is through a BVNet. And BVNet is basically a series of 2D convolutions and MLPs. And finally, we predict the future have poses through another MLP. And our entire network is supervised by a combination of L1 losses on the translations plus L1 loss on the rotations. Cool. So next, let's talk about data. So we need data that first contains post-egocentric RGB videos of real-world navigation scenarios. And it needs to capture both static and dynamic obstacles. And it also needs to display the information gathering behaviors that we desire. So we first look at prior datasets. And first, autonomous driving datasets like Waymo Open that has real-world navigation scenarios, provide 3D bounding boxes, but they do not provide egocentric observations from the pedestrian's viewpoint. And next is virtual humans, for example, Egogen. And they deploy synthetic human motion generation algorithms in a set of 3D synthetic environments. And they can render out whatever observations we need. But limited by the progress of the human motion synthesis algorithms, these motions are normally simple and are also rendered in simpler environments as well, which creates a large distribution shift. And lastly, Meta itself has released several datasets with their project RVL glasses, and one of the closest is Nymeria. So Nymeria also captures data from the real world, has egocentric observations from the glasses, but as we dig into the dataset, the scenarios that the dataset features are mostly collaborative scenarios. For example, in the navigation setting, if there are multiple people walking, it's mostly these people are walking together alongside each other instead of against each other. So this is a relatively narrow distribution in the navigation scenario, and also creates a distribution shift from the navigation tasks that we care about in real life. So given these, we decided to collect our own dataset, which we call ARIA Navigation Dataset. So we want our data collection pipeline to be as scalable as possible. So the collection hardware is only a pair of ARIA glasses. It captures RGB videos and IMU readings, which are later used for SLAM. And our dataset contains 4 hours of recordings covering 18 relatively densely populated places. And each recording section actually only takes a few seconds to set up. So it's very easily scalable. And now let's take a look at the qualitative results. So here I'm going to show a video, and we'll render out a few things. So the green stuff means ground truth, and red means model predictions. And the 2 squares in the middle are the camera frustums, either predicted or ground truths, projected in the current frame. And these curves on the ground are the ground projected translations. So these are the 2 things. So I'm going to pause, or the video is going to slow down at several key moments. For example, here, when it sees a large crowd of people coming on the right side and there's really no viable path, the model predicts that it should slow down or wait. Maybe it's not as very clear, so let's see that again. So originally there is a very clear path representing the velocities, and as the people approach, it predicts that it should wait, and then as the people go by, it says, okay, let's go again and surpass the current group of people. So yeah, then let's wait. So there are a couple of such moments that it exhibits the waiting behavior. Here it is again. So it tries to surpass the people from the left first, but eventually as I was going to the right side, it converges to the other mode. Here's another case of waiting. You can also notice that all of the faces were blurred. All right, cool. So I think, okay, here's another group. So next, we will notice there is a information gathering behavior, as we said. So as we are about to cross the road, the model predicted that we should rotate our head to check for incoming traffic in both directions. And then we finally cross, and yeah. So as we can see here, the model has developed some of the desirable behaviors that we want. And all of these are through data-driven learning. So yeah, here is just a collage of more examples showing our data captured in different locations, lightings, weather conditions, or time of the day. So here are some picked scenarios that shows those behaviors that we just talked about, like waiting in the first row, or information gathering through head turnings in the second row, or in the last row is path adaptation, which the model tries to adapt its path based on the new information available, which is this person. I think due to time reasons, I'll just, this is the last slide, second last. So some of the failure cases that because this model is not generative, so it doesn't quite predict the multi-modals. This is something that needs to be improved. And also for some of the rare scenarios seen in the training data, for example, this railway, the model fails to recognize that there is railway here, and thus it should actually check for the surroundings or slow down speed or like recognize that height difference from the ground. But yeah, that's it. Thank you for listening, and here's the QR code for the project page, and here's the poster information if you're interested. Thank you.
Thank you. Hello, everyone. My name is Gen. I'm a PhD student at ETH Zurich. I'm very honored to have this to have this opportunity today to present my work. I would discuss the efforts that we are making to build a multi-modal egocentric foundation model. We humans express and interact with the world in a multi-modal way. So to truly understand humans, a model needs to understand diverse modalities, such as body motion, hand movements, gaze, as well as the visual data captured from an egocentric perspective. However, current multi-modal models mainly focus on egocentric question answering and typically only focus on modalities like video and text. So they lack 3D and 4D understanding abilities and fail to incorporate important human-related modalities, such as human motion and intention. And empirical scaling law just have guided large-scale training, but a major bottleneck is the availability of large-scale and high-quality datasets to support such progress. But collecting real-world data with accurate ground truth annotations is very expensive and non-scalable. Then the question is that, do we have enough data to scale up the egocentric 4D training? My first PhD work focused on generating large-scale egocentric synthetic data with accurate and rich ground truth annotations. It is called EgoGen, an egocentric synthetic data generator. So this is an overview. It is done by first generating the embodied human motion navigating a 3D scene, and with a generative human motion model, and render the egocentric perspective of synthesized motion sequences. And we show that with EgoGen, we can scale up the training of egocentric multi-modal multitask in this work, EgoM2P, egocentric multi-modal multitask pre-training. So multimodalities provide different perspective to understand egocentric vision. The depths represent 3D scene around us, and gaze encodes human intention, and camera trajectories represent human head motion. multimodalities complement and interact with each other, and understanding egocentric vision needs multimodal learning. The egocentric vision is also evolving with increasing datasets. The real-world data provides semantic-rich and diverse data sources, and the synthetic data offers precise ground truth annotations, and they are very cheap to scale. And it's more and more feasible to train a large multimodal, multitask egocentric vision models. But egocentric datasets are captured by heterogeneous devices and cover different modality annotations. We train our model with 8 egocentric datasets shown in this table, and you may see many modalities are actually missing. To handle the unaligned data, we use masked modeling. In addition, compared to existing multimodal image foundation models, we need to handle the temporal consistency due to the fast-changing camera poses, and also spatial temporal complexity introduced by frequent human-scene interactions. Our model also needs to process video tokens, which contain far more tokens than images. First, we train a transformer-based VQVE tokenizer for camera trajectories and gaze dynamics to learn motion priors. We'll later show that the learned motion prior helps the model to predict natural egocentric motion. And our unified tokenizer architecture is extendable to evolving egocentric multimodalities such as ego hand motion. And with the recent video tokenizers, we tokenize all data into 4 billion multimodal token database. For the main model training, we use both input masking and target masking. We set the maximum number of visible tokens and target tokens to 2048. So the maximum number of visible tokens should be big enough to accommodate enough video information for the model to learn, but it also should be small enough to make this task difficult to push the model to learn some deep representation. And we use directly distribution to randomly sample multimodal tokens during training. And this makes sure that our model is trained with variable masking rates. And this is a very good property for fast inference. We also make sure that the target tokens doesn't overlap with the input tokens, and the model should predict masked tokens based on input visible tokens. And with randomly sampling and masking, the combination of visible tokens change during training. The total number of training tokens is 400 billion. And the main model architecture follows encoder-decoder-based transformer architecture. And the encoder fuse spatial temporal information from multimodalities, and the decoder performs masked self-attention to tokens within the same modality. And the model is trained with 256 H100 GPUs for 16 hours. And during training, we use variable masking rates. As a result, our model can benefit from the parallel decoding, and our model can reach more than 300 FPS inference speed for egocentric camera tracking. Our model is able to multitask. The first task we show is egocentric gaze estimation. The blue circle is the ground truth, and the yellow star is our prediction. We can see that our model is able to better understand human intention than specialist baselines. The second task we show is egocentric camera tracking. The black wireframe is the ground truth. So compared with specialist state-of-the-art baselines that require expensive geometry test time optimization, our model predicts smooth and plausible camera trajectories in the sense that it learns to capture the uniqueness of egocentric head motion. And you can observe the joint slam result. The prediction is shaking all the time, but the camera is attached to the human head. The actual human head motion doesn't shake. And we then show our strong generalization ability to unseen datasets, the area digital twin dataset, which is excluded in our training. Our model effectively predicts realistic egocentric camera trajectories. The third task we show is egocentric depth estimation. So as a video model, our model achieves better temporal consistency. As you can see, the depths flickering in the baseline methods. We also show our strong generalization abilities to unseen datasets HOI4D. The rolling depths fail to predict hand geometry, and Alliance 3R fails to preserve temporal consistency. We compare the depth-conditioned egocentric video synthesis with control net baselines. So even though they are initialized by the powerful stable diffusion, they tend to hallucinate and produce the wrong finger motions, as you can see in the second row. And their synthesized videos are out of the distribution of egocentric videos. And our results show improved alignment with the input depth video and minimize hallucination. Lastly, we show a qualitative comparison with Megasam. Unlike Megasam, which relies on the state-of-the-art monocular depth estimators and expensive geometry test time optimization, and requires 71 seconds for this single example, and our model efficiently reconstruct dynamic egocentric scenes in a feed-forward pass and need less than 1 second. We perform ablation studies on EgoGen, and EgoGen can offer large-scale synthetic data with accurate depth and camera pose annotations. And we can see with EgoGen, we can boost the EgoM2P performance on both depth estimation and egocentric camera tracking. In summary, in this work, we show that egocentric synthetic data can help data scaling, and EgoM2P remains to evolving datasets and new heterogeneous modalities such as hand motion or ego body motion. And we test the model on many unseen datasets, and we show it has promising zero-shot capabilities. We are very happy to discuss our work with you at the poster session. Looking forward to seeing you there. Thank you.
Thanks, everyone. So yeah, I'm Robin, and I'm going to talk a bit about egocentric motion synthesis and the GORP dataset. So maybe to set the stage a little bit, this is a small demo of the current system that exists that you can use if you're a developer in the VR world. So basically, you can drive an avatar from using the egocentric sensor of the headset. This is a sample that you can download and build in your Unity scene, and I would really encourage you to try it if you're interested in that types of technologies. So what you can probably see is that we support a relatively diverse set of motions with this type of technologies, even in real time. However, the motion doesn't look exactly as good as a human motion. You can still see that things are a bit robotic. And it's not only because there is a robot asset here, but that's kind of the problem we're trying to solve here. So there's different way to look at this. One of the most popular way, and it's what we've seen, I think, a lot today in this workshop, is the egocentric body tracking approach, where you have a specific device, for instance, AR glasses. You have a camera stream, and you have this tracked head pose that comes from the SLAM system. And then the goal is really to try and take these two inputs and estimate the pose as much as you can. What I'm interested into is a slight reframing of the task, is to actually start thinking about any device configuration. You don't really care about the sensor set anymore. And then don't look at the image directly, but instead look at tracked body joints. So the idea here is that vision starts to work pretty well. For instance, we discussed a bit earlier today that ARIA Gen 2 is giving you hand tracking, so you don't need to learn hand tracking in your model. So the idea is that we are more interested into not looking at the vision challenges of scene understanding, robustness, sensor set, but more into addressing the remaining part about the motion quality. How do we close the gap on this remaining motion to make it look good, and as well as a real motion? And also a difference here is that the final goal is not so much to estimate the pose accurately, but more to drive an avatar, which actually changes a bit the way you look at things. And I will go into the details a bit later. In this egocentric motion synthesis task, maybe the most common occurrences, this is what's called a 3-point synthesis. So I give you here 3 example papers looking at this. And on the right, you have these demo videos from the codebook, categorical codebook matching problem, which is a great occurrence of that type of work. So here they use the 3-point because you have the headset tracking and then you have like signals from the controllers. If you look at the different papers in that field, everybody's working from mocap types of data sets. So typically AMAS, and then they demonstrate on some real recordings but there is no like clear data set on how to do that. Everybody's recording their own sequences and it's hard to compare side by side different types of models. Also, I'd like to illustrate a few challenges that we have in this field of egocentric motion synthesis. The first one is the temporal sparsity. So typically what happens in a system like this is that you have the headset or the glasses, you have a camera stream, and then you would have like one model, like a SLAM model to get you the six DOF track heads, and then maybe another model to give you 6 DOF track hands. However, as we also discussed a few times here, is that the camera don't have view on the full body. So you really get some body signal, in particular for arms and hands, in a very temporally sparse way. So if you look at the motion on the right here, you can see it's like somebody waving their hands, but as they wave their hands, the hands kind of like disappear from the sensor, and then you don't really know what is happening. So it's kind of like you need to be able to train models that are not bothered by this temporal sparsity of like limbs coming in and out of the sensor field. Another interesting problem that is not very well studied, in my opinion, is the body scale ambiguity. So many approaches assume that you know the user scale. You load it from the ground truth. In practice, it's not really the case. You cannot ask a user to do like a full body registration in a mocap studio in order to be using your system. So either you need to be able to estimate it online as you perform some motion, and then you need to be able to progressively build an understanding of what the body look like, or use some kind of registration stage, but then this is going to be imperfect. The scale is going to be noisy, and you need to have a system that is able to cope with these types of scale noise, scale robustness, and challenges. And there is always when you have these types of systems that don't have a lot of sensing, there is also a big ambiguity between scale of motion, because depending on the body scale, you don't know if this is somebody standing or sitting, for instance. So this also is interesting to study in that field. Another one is that bodies also have hands. So in practice, a lot of people are looking at the body because hands is like another field almost. But in practice, there is also an interesting need, in my opinion, to start modeling motion together with hands. There are some motions that I'm trying to illustrate on the left where it's actually pretty interesting, where there is a strong correlation between hand pose and body pose. So if you start crossing your arms, or interaction between your hand and your face, and if you see here, this is typically the types of motion where you don't have a lot of visibility into the sensors. So you really need to rely on some kind of synthesis model or like a non-vision based approach to try and reconstruct these motions. And of course, when you start talking about hands, this creates also open problems about penetration between hands and the body when you do these types of hand-hand sequences. And finally, maybe another interesting challenge is how do you evaluate these types of model? So if you try to do tracking for inputs, it's pretty clear you want to match the ground truth as well as you can. But if you try to create motion to drive an avatar in a natural way, your objective is a bit different. And probably the body tracking metrics, the standard ones, are not so useful anymore. What we actually want to do is more to favor a bit plausibility over accuracy, and focus on also preserving the motion semantics. So typically on the right here, you have an example of the crossing arm sequence. So this has to be fully generated because you don't really see it's not very visible to the sensors. And if you think about these types of motion, when you cross your arms, whether you track it with one arm up or down, it doesn't really matter. What you want to convey is kind of the semantics of this person is stretching their arms. And also in practice, some types of artifacts, like the feet here snapping, even though they only move the feet by a few centimeters, this is creating very visually disturbing artifacts that is breaking the immersion. So here also it shows that positional accuracies is not enough to kind of compare these different models. So we've collected the dataset, the GORP dataset that we released in CVPR 25 to try and study these types of these types of problems, sorry. So the dataset is actually the first dataset where we use, where we have together real tracking signal paired with high quality ground truth using mocap. So the way this works is that participants are wearing a headset, Quest 3 headset, and we are using an OptiTrack-based mocap system to generate the ground truth, and they are running a real VR session. So they are playing a bunch of popular games in controller modes, in hand modes, and then this is synchronized, and we can get a ground truth of all of this. We also have participants, about 30 participants of diverse height that also can help you understand and model these types of scale-related problems. There is about 14 hours total of gameplay, which is relatively large for these types of datasets, but also I think it's still relevant to use the standard approach of like having a large mocap dataset to kind of pre-train things and use this as like a test set or a fine-tune approach. So yeah, you have the code here if you are interested too. Oh yeah, and also, sorry. So in types of, this is the ground truth, and then for inputs, we have obviously the head tracking system, but also the controller tracking, and then the hand tracking system, the hand tracking outputs as well, to give you these types of temporal sparsity that I was mentioning. To give you an example of what we can do from these types of data, so this is the paper that we published last year in CVPR. So you have example here on the right of temporal sparsity. So typically, when the user does some types of motions, the hand tracking signal would disappear, and as it goes out of the field of view of sensors. Just to explain a few words, this example of what we try to build from this. So we are specifically looking at the temporal sparsity problem that I was describing at the beginning. So how can we generate motion that smoothly transition when the tracking systems goes on and off? And this approach, so it's an autoregressive diffusion approach that is basically built around the concept of rolling prediction. So the idea is that you have, instead of directly predicting the pose, we are predicting a buffer of the pose in the future that we are progressively refining as it comes toward the present. So kind of like progressively disambiguating the motion. And by actually predicting this future motion state, we show that the model managed to learn some kind of planning capabilities, and it learns to transition as the tracking system is coming on and off. Yeah, so this gives you an example of the purple lines that are the predicted future motion, and as the tracking signal comes back into the field of view, the model. Let me show this once again. So here the hand is not visible to the sensor, and as the hand is gonna get back into the field of view, the model is learning to transition smoothly toward this new tracking signal. So when you locomote, obviously it's kind of like plans the motions. And here is also an example of, I think, tracking loss, synthesis, and then transition again toward the tracking loss when it comes back. And yeah, and so back to the example I was showing in the beginning. So this can help you capture these types of motion where we are not in the field of view anymore, and we still maintain a high quality pose. All right. So yeah, so this is a dataset that we very freshly released, and we'd like to start to draw a bit more attention into using these types of data. So ideally, we would like to start and maybe try to do a challenge around this task and have accept some paper submission with a future iteration of the EgoMotion Workshop. So if you are interested, request a dataset, reach out your interest to participate to these types of work, yeah, so we would share the dataset, have some specific hidden sequence, and also work on qualitative evaluation to give feedback about what types of artifacts we see and how we can compare different types of motion. So yeah, if you're interested, reach out and download the dataset. Thank you.